Good afternoon.
Good afternoon, sir. Good afternoon. Sir, shall we start?
Yes.
Yes, sir. Yes. Bobde, sir, please introduce, sir.
Oh. Good afternoon to all. Today's speaker, Dr. Masagar, sir, Professor, Dogra Chair and Head, Department of Civil and Environmental Engineering, IIT Delhi. Sir has obtained his doctorate degree from IIT Bombay in 2005 in the area of earthquake engineering. For his PhD thesis titled Earthquake Behavior and Impact Response Control and Base Isolated Building, for which he has been honored with the IIT Bombay Research Paper Award. He performed postdoctoral research in the area of application of carbon fiber reinforced polymer composites in prestressed concrete bridge structures at the Lawrence Technology University, Michigan in the USA. Professor Masagar sir's current research interested include the multi-hazard engineering, blast, fire and wind engineering, then earthquake engineering, structural dynamics and vibration control, computational finite element methods, fiber reinforced polymer in the prestressed concrete structures, bridge engineering. Related to this research area, he has completed number of sponsored research projects in national and international collaborations. He has developed innovative technologies in these areas, some of which are copyright and patented, and he has been actively engaged in the field implementation of these technologies in real-life construction projects in India. He has published 165 international journal papers, 13 book chapters, 158 international conference papers, 3 books, 5 edited proceedings, has 2 patents and 1 copyright. These research contributions have duly complemented in his teaching, enriching teaching and learning. He has guided several students at both UG and PG levels in their bachelor and master projects and doctoral research. Besides UG and PG student guidelines, he is actively engaged in sponsored research and consultancy projects at national and international levels. Sir is the recipient of numerous national and international recognition, including these also Fulbright Kalam Climate Fellowship for Academic and Professional Excellence, Humboldt Research Fellowship for Experienced Researchers, Carl Friedrich Owen Simmons Research Award, Erasmus Mundus Award, Erasmus Higher Education Fellowships, FEIT Visiting Academic Fellowship, DST Young Scientist Award, DAD Research Ambassador and DAD Awards, DAE Young Scientist Award, IBC Award for Excellence in Built Environment, IEE, IEI Young Engineering Awards, IIT Delhi Teaching Excellence Award, IIT Delhi Outstanding Young Faculty Fellow, Young Professional Award, CIDC Vishwakarma Award for Academicians. He has served as a member on the National Building Code of India and is currently serving on code development committees in the Bureau of Indian Standards, Indian Road Congress, and international standards organizations. He is National Coordinator for Civil Engineering and Allied Subjects in the Swayam Prabha DTH channel. Currently, Sir is serving as a core member of Program Advisory Committee, Civil Infrastructure and Transportation Engineering of the Science and Engineering Research Board, Government of India. Currently, Sir is serving as editor-in-chief of the Indian Concrete Journal. He is associate editor for the computational methods in structural engineering section in Frontiers in Built Environment. He is the editorial board member of the Bulletin of the New Zealand Society for Earthquake Engineering, proceeding of the Institute of Civil Engineering, Structures and Building Advances in Civil Engineering, International Journal of Protective Structures and Journals of Architecture, Structures and Construction, a guest editor of journals, namely Institute of Engineers, India, Shock and Vibration, Frontiers in Built Environment, Journal of Low Frequency Noise, Vibration and Active Control. Serve as the editor-in-chief of the Indian Society of Earthquake Technology Journal and responsible editor of the Earthquake Spectra Journal. Sir is founding director and fellow of the Council of Vibration Specialists and incumbent vice president of the Indian Society of Earthquake Technology. Sir is also an elected fellow of the National Academy of Science, India, Maharashtra Academy of Science, Indian National Academy for Engineering, Coalition for Disaster Resilient Infrastructure, Institute of Engineers, and Indian Society of Earthquake Technology. Dr. Matskar, sir, over to you.
Thank you for that introduction. Earlier, when my introduction used to be read, I used to say that there is no need of reading the introduction so long. But nowadays, I have stopped saying so because some students contacted me and they said they would like to hear all these details so that it becomes an information for them as to what career aspiration or professional aspirations they should have. So therefore, I'm grateful that this uh, biography has been read. Before I begin, I'm grateful to the head of the Department of Civil Engineering, SVPM, to give me an opportunity to have some interaction with the faculty colleagues, and I can see large number of them have joined this faculty development program on a very, very niche topic of building sustainable infrastructure for urban and social resilient challenges and future pathways. Before I go forward, I would like to confirm whether you are able to hear me properly and my slides are visible to you. Please, anyone,
Yes, sir.
you confirm?
Yes, sir. Yes. Yes, sir.
Okay. So in this 1 week Atal FDP program, I'm given to talk about some challenges faced in the design of earthquake resistant structures. And the topic itself is significantly vast. And therefore, within next about what I understand is 1.5 hours, I will give you some glimpse of it, particularly in the context of recent change made in the uh, country's new um, Code for Earthquake Resistant Design of Structures, Indian Standard 1893. So in that context, let me directly dwell on the topic, the reason being that the time is short. Typically, we design the earthquake resistant structure with a certain presumption made, some assumptions made while we are doing it. One of the major assumption is obviously we want to ensure the life safety, but at the same time we have to also ensure that the design of the structure is economic. Therefore, common people who probably doesn't much understand earthquake engineering, they say that please build my house earthquake proof. But obviously, we do not build structures earthquake proof. We design the structures for their resistance to design earthquakes. The objective behind that is that during some frequent minor shaking, there should be no structural or non-structural damage. Whereas once in a while, when major earthquake happens, there could be some damage, but again, the structure should not completely collapse, so that people using that structure should be able to evacuate the structure in time and there will be no loss of property as much as possible. There are different scales of quantifying the damage and deciding the level for which the design of the structure should be made. And accordingly, our standards are being modified period and again, incorporating some of the latest knowledge. And the recent version of IS 1893 2025 is one best example of that as to how new knowledge is contributing towards development of new codes, which on one hand side helping to economize the design of the structure, whereas on the other hand side it is helping us to protect invaluable uh, life of people. Now, it has a serious design implication, and depending on the type of structure, we decide how much protection we need. For example, if there are lifeline structures, we need to ensure that they should not fail because the consequences of their failure are enormous, such as the dam structure, for example, or nuclear power plant structures. Whereas some essential facilities, which we call them as lifeline structures, they need to remain functional because during the earthquake and immediately after the earthquake, we require them the most. And therefore, we have to design these lifeline structure for their operational level of seismic safety. When we do so, invariably we are talking about performance-based design. Though Indian code is yet to adopt the performance-based design, however, we need to design them in order to meet certain seismic performance. The Western code, for example, they have already shifted over to performance-based design, and over a period of time, India will also shift to the performance-based design. Now, the today's topic, the challenges. Uh, I would rather say that there are not some significant challenges as such, but I'm talking about overall challenges and putting the whole thing in a perspective. For example, one of the challenges of not being able to adopt the performance-based seismic design in our country as compared to the Western country is the data of seismicity or the hazard levels was not fully known to us. Now, gradually, we have started doing microzonation, we have gathered the data, and now our zoning map has been changing from the deterministic to probabilistic zoning map. So that is one example I would like to give to tell you that how the codes are developing over a period of time. And I would like to draw parallel with what is happening in case of concrete design code, which all civil engineers are fully familiar with, or steel design code, again, civil engineers are fully acquainted with. During the olden days, about 2 to 3 centuries back, Indian standard IS 456 was working stress based approach, whereas the limit state approach was just one of the chapters. Over a period of time, there are significant changes, and now working stress chapter becomes one, and the remaining part of the code remains as a limit state page. Similar thing has happened in 2008. The earlier IS 800 design of rolled steel structures was based mainly on the working stress design approach or allowable stress design approach, whereas there was only one chapter which was on either LRFD, load and resistance factor design, or limit state design. In 2008, reverse has happened. Only one chapter is on working stress method, and the remaining all chapters are based on LSM or limit state method. What it indicates to us is most of the codes are gradually changing from deterministic to probabilistic, and similar is going to happen in case of IS 1893. And again, example from IS 1893 that I have given is the zoning map has now changed from deterministic to probabilistic. Therefore, we will also talk about probabilistic seismic hazard assessment and probabilistic seismic design of structures as we go along, and this code will now probably change very frequently. I have the fortune of serving as the code committee member of Civil Engineering Division CED 39 committee, and there we do deliberate on these matters, and in particular our meetings are now very periodic. Every month at least there is one meeting, and we ensure that all the obsolete codes and obsolete information from the codes is being completely replaced with the new information, and the code is revised very frequently nowadays. Whenever we reach up to a certain stage, a certain milestone, we publish the code and make it available for designers to design with them. That design that we understand for earthquake resistant design in particular, we understand that the capacity of the structure needs to be significantly higher than that of the demand. So we always compare the capacity and demand, and the ratio of that is essentially the factor of safety. Capacity is how much the capacity the structural elements has to resist the earthquake induced forces, and earthquake induced forces tells us what is the demand from a given hazard, which is earthquake in this case. Now, typically with the severe shaking, it might not be possible to resist everything under the linear zone, and therefore we go into non-linearity, and thereby we need to rely more on inelastic response of the structure. And mostly our earthquake resistant code is on inelastic design or inelastic response of the structure. So typically, we talk a lot about response reduction factor, and that response reduction factor is directly related to inelastic response of the structure. Our code is also based on now what is the vulnerability, which is basically what is the probability of failure in different modes of failure at different site locations. What is the exposure level that also is taken into account to evaluate the risk associated, and obviously it depends on how severe the shaking is. So you might have heard some of these terms such as vulnerability or hazard or fragility, resilience, exposure, and so on. More or less directly, these terms are now being used in our code. About 2 days back, we had a national level meeting of National Disaster Management Agency. And for different part of the country, now we are in the process of developing risk, and risk map will be developed eventually for the building stock as well as the community resilience. Of course, we have long way to go, but India is the first country where this initiative has started as to how we are quantifying the risk, and that will help the local authorities to plan for the infrastructure in a given locality. Obviously, we understand that the risk depends on how frequently and what kind of earthquake happens at a locality, what kind of buildings are built, whether they are poor buildings, poorly built buildings, or the material is not so good, or the material is reinforced concrete and very well built. And exposure is how much population resides at a location, and depending on that, risk is calculated. Earlier, India did not have a lot of strong earthquake ground motion data available, but nowadays there are some repositories where this data is available. Typically, this data is important for us to know what is the peak ground acceleration to quantify the intensity parameter of that earthquake. So in a locality, we find out as to what maximum ground acceleration has reached during some significant earthquake, which we call as a strong ground motion. Because for geologists and seismologists, even the normal ground motions are important. But for structural engineers in particular, strong ground motions are only important because they affect the structure more, and the usual small tremors do not affect the structures as such. And that is quantified using the intensity of an earthquake. And we quantify that actually based on three parameters: peak ground acceleration, which is abbreviated as PGA, frequency content, and how long that earthquake has stayed. Nonetheless, the frequency, content, and duration are taken indirectly into account, whereas peak ground acceleration is directly taken into account in the design of structures. These are some of the examples of ground motion, and there are some samples available in the literature how these digital or earthquake ground records in real time looks like. There is a specific reason why I have brought to the discussion that these are the digital earthquake records available, because now in the IS 1893 there is a specific mention of site-specific response spectrum. Now, if we have a site-specific response spectrum made for a given site for an important structure, and if we are asked to carry out nonlinear dynamic time history analysis, we need suits of earthquake. Let's say we need 30 earthquakes, and those earthquakes should be spectrum compatible. To make them spectrum compatible, we are required to use certain factors, and in different approaches we use, for example, these digital earthquake records, and we scale them to make them spectrum compatible. That is one approach. The other approaches are to develop the artificial or synthetic earthquake time history. Again, it requires some advanced tools to make the earthquake time histories and make them compatible to site-specific spectrum. Again, these advancements have happened in last about few decades, 2 to 3 decades, and now they have been incorporated in IS 1890 2025. There are total of three design approaches: equivalent static approach and dynamic approach. And out of that, the response spectrum approach is relatively popular. Even in the equivalent static or seismic coefficient approach, the spectrum needs to be used. Now, the response spectrum, as we all know, we have the time period of single degree of freedom system plotted on the x-axis, and on the y-axis we have the pseudospectral acceleration values plotted. And if it is a real earthquake, then we get the red color one, zigzag with peaks and valleys type of curve. But for design, obviously we need a smoothened curve, and therefore we have that blue color curve, and it is a specification. It is a design specification given by the Indian standard. And again, there are significant changes made in this response spectrum given. However, most of our designs in the country are based on the what kind of response spectrum is given, and structurally speaking, depending on how flexible or how stiff the structure is, its acceleration values could be higher in the range of acceleration control zone, or if it is a very, very flexible structure, it means time periods are higher in the downstream side of the time period axis, then the spectral accelerations values are lower, and the design of the structure is mainly governed not by the acceleration but by the displacement response. As I have mentioned earlier and emphasized quite significantly, our IS 1893 majorly relies on inelastic response of the structure. So when I teach this course of earthquake resistant design of structures to my students, I tell them that if you are explaining this concept of earthquake resistant design of structures to a layman who doesn't fully understand as to how the code specifies earthquake resistant design, I mentioned to them that explain to the layman that instead of making the columns bulkier, stronger, we make them actually weaker. The reason we make them weaker is we want them to go into inelastic zone so that significant amount of energy is either absorbed or dissipated within those column members, and we allow them to fail, but then we designate as to which column should be allowed to fail. Thereby, all the seismic input energy is dissipated there, and remaining structure stands okay. And then after the earthquake is over, those locations which are extensively damaged can be replaced. So this is a overarching philosophy of earthquake resistant design, and therefore we apply what is called the response reduction factor. Now, if we apply the response reduction factor, we are actually reducing down the capacity of, or the linear elastic capacity of the member To force that member go into non-linearity means we are forcing from here onwards the member to go into significant inelastic response or damage. So we have calculated damage introduced in the structure. So this is the fundamental philosophy with which we design the structures. And there are total of four fundamental virtues of earthquake resistant design of the structure that our Indian code relies on. And they are strength, stiffness, ductility, and configuration. And my today's presentation will essentially revolve around this, giving some highlights of the change in the code, what provisions have changed, and then what is the background of that, and how our practice is going to be influenced because of that. While we take into account the response reduction factor, we account for the ductility that we want in the structure, how redundant the structure is, and the manufacturers or suppliers or the building materials. They give us the material with certain factor of safety of the strength, so to account for the overstrength. And total, we calculate the response reduction by what factor it should be reduced, and those becomes our design values or design forces for which we design the capacity of the members. Here we have to essentially quantify the ductility that the structure would provide, and we calculate that response reduction factor based on what ductility we require, and then we have that design force calculated as what is the maximum elastic force that member can take divided by that response reduction factor. One can very easily understand this concept if uh, this is clear that if it is a very good structure, for example, special moment resisting frame, then you need to reduce down its response quite significantly. Therefore, R factor for that or response reduction factor of that needs to be quite high. Whereas if it is a poorly built structure, and I'm just giving one simple example for the sake of comparison, if it is an ordinary moment resisting frame, then the R factor is lower than the special moment resisting frame. So this explains the concept behind the response reduction factor, how it helps us to achieve the ductile response of the structure rather than the elastic response. Thereby, we have the larger amount of energy dissipated in either cracking or rupture or failure of the structural members. The entire philosophy is based on, of course, design of the lateral load resisting elements, and essentially we focus more on two lateral load resisting elements, and they are columns and shear walls. May I request the organizer to kindly mute all the participants? Can the organizer confirm that all the participants are muted right now?
Yes, sir. Yes, sir.
Please mute everybody. This is
Yes,
not a
sir.
question, answer, or interaction session.
Yes, sir. Yes.
Thank you very much. We essentially design the lateral load resisting elements because during the earthquake ground motion, it is the ground which shakes, and because of that, horizontal forces are induced in the members because of the inertial action. And because of that inertial action, the members are required to resist the horizontal direction forces, and therefore we always talk about design of the lateral load resisting elements, which in this case are columns and shear walls. In order to calculate for how much force or what should be the demand for which it has to be designed or this capacity has to be designed, there are different approaches available. Our code earlier used to talk about these three approaches: seismic coefficient method, response spectrum method, and time history method, whereas more emphasis was given on the seismic coefficient method. However, in the latest revision, gradually more details on how to conduct the time history analysis or nonlinear time history analysis has been incorporated, and more information has been given. And most importantly, now there are some suits of earthquake time histories given in order to help carry out the time history analysis of the structures. Nonetheless, in the practicing engineering community, seismic coefficient method still remains one of the most popular approach for designing of structures. Whereas for very important structures, the code mandates that nonlinear dynamic time history analysis needs to be carried out. One of the major change which is very extensively talked about in the country of late is the change in the zoning map. And in the beginning of my talk today itself, I have talked about as to what is the significant change in the IS 1893/2025 that has happened based on the more information available to us on what kind of hazard we receive from the earthquake viewpoint, and we have changed over from the deterministic seismic hazard map to probabilistic seismic hazard map. All of you would definitely understand for us to change over from deterministic to probabilistic, we needed data. And when data was not available, we relied on the deterministic zones. And now when the data is adequately available, statistically available, then we have now graduated from deterministic to probabilistic seismic hazard assessment, and thereby our zones have changed. Now we have from zone 2 to zone 6, and thereby we have 5 zones. And earlier we were mainly talking about the lateral load resisting elements, but nowadays we have also started talking about the long spans elements. For example, if it is a mall or some theater where there are long span beams and they are vulnerable against the vertical component of the earthquake ground motion. Therefore, now the design-based equations are given for two cases: horizontal earthquake ground motion and vertical earthquake ground motion. And here essentially we multiply the seismic weight of the structure by some coefficient, and that is where the name has been obtained, seismic coefficient method. And that coefficient that we calculate when we had no codes available for earthquake resistant design of the structures, the coefficient we used to take is 10. What it means is that whatever is the total weight of the structure, we used to divide it by, we used to take the 10% of it, means zero point 0.1 times the total seismic weight, and we used to design for that. And those structures, they survived most of the fury of the earthquakes. But obviously, if we now compare that 10% of the seismic weight is quite high an estimate. But of course, in absence of the research data, that was a very good estimate. But now that 10%, instead of taking that arbitrarily, now there is a science behind that, and based on that we now take a particular fraction of the total seismic weight in the gravitational, means vertical direction, to apply it in the horizontal direction. And that science basically is dependent on what kind of zone factor we use, which is a function of p ground acceleration, again probabilistic, based on the probability, how important that structure is, and then what kind of inelastic response we need to force the structure to go in. And we do that for only the first mode of vibration. Obviously, this is a equivalent static approach, and therefore vibration mode doesn't directly come into picture. We calculate these time periods based on some thumb rules, and again those time period equations have been improved over a period of time. The earlier version of the code before the present version had design basis earthquake and maximum credible earthquake. Now that part has been completely removed and it has been replaced with, if you would like to compare that with, as a design basis earthquake. Means everything is for the purpose of designing the structures for a given level of earthquake hazard. One of the most important concepts introduced in the new code is the return period. And the way I have arranged the slides in today's presentation is, first of all, I'm highlighting what are the changes, and then later on in the later slides, you will see why we have done so. So I will explain about as to why the return period based zoning has been given depending on how important the structure is. But just to explain to you as to why it is done very quickly is that whenever a significant earthquake happens, its frequency of occurrence, means how many times it occurs in a given time duration, is relatively lower. Whereas small tremors, low intensity earthquakes, they happen more frequently. They happen now and then. For example, again, this is more of a layman's explanation as to what is the meaning of return period of an earthquake. A magnitude 3 earthquake may happen, let's say, once in 5 years in some location, let's say in Indore. But a magnitude 5 earthquake may happen maybe once in 50 years or 100 years. Or a magnitude 6 earthquake at the same location may happen in once in 1,000 years. So as the magnitude of the earthquake that we are talking about is more, it takes significant amount of time for the earthquake to happen to that intensity. Whereas some very, very small earthquake in terms of their magnitude, they happen relatively more frequently. That is the concept of return period. It means more the return period, higher the magnitude we are talking about for which the structure needs to be designed. So for the dam structure, for example, or nuclear power plant, higher return periods are required to be used. Means the probability of occurrence also needs to be considered higher. Whereas for routine structures, we can take the smaller ones and thereby their coefficients would be also lower. So accordingly, you will see in this table given in IS 1893-2025, for the lower return periods, the coefficients are much lower to the extent that the lowest one is 0.0375, and for the higher ones in the severe most zone with the larger return period, it goes all up to 1.125. Please note that this is in the numerator, means the horizontal earthquake coefficient becomes higher. The multiplier is, in earlier case it is 0.0375, and second case it is 1.125. And within this, now we are able to achieve economy of the structure depending on what type of structure we are designing. I have taken one example of the spectrum. The spectrum has also changed. Earlier, the spectrum was not up to 10 seconds, but now the spectrum has been given up to 10 seconds because typically long span structures such as bridges, their time period could be higher, and thereby we have also included the longer time period of the structure. Obviously, we have the acceleration control structures, somewhere here velocity control structures, and somewhere here they are acceleration control structures, and we have displacement control structures, and we have given this for both the elastic response spectrum method and the time history analysis as well. Then there is some discussion still going on to further revisit the response reduction factor, but I have already talked to you about if the structure performs very well, it is very well built structure. Typically, the response reduction factor is higher, and I have given you the example of special moment resisting frame for which the response reduction factor is 5, and relatively poorly built structure. For example, I have given you that of the ordinary moment resisting frame. The response reduction factor is 3 because it is easier for OMRF to push it into inelasticity, whereas it takes more force or more efforts for SMRF to put into inelasticity. Our intent in the philosophy is that we need to essentially have inelastic response of the structure so that the total input energy is dissipated there. Similarly, we have the provisions for how many people are using that structure at a particular time. We cannot assume that the entire structure is full of people, and therefore we have certain norms in order to reduce down the design. This helps us to economize the structure without compromising with the safety. And then we calculate the total horizontal force acting on the structure and then the base shear on the structure. And then we divide that among the different lateral load resisting elements at each floor. And this seismic coefficient method has certain assumptions in this case. Typically, we assume some small span structures, and thereby the floors, means the slabs that we consider, or ceiling if we see from bottom, so they we consider them as rigid so that their deformations are not taken into account, whereas the lateral load resisting elements such as the columns and shear walls, We only design them for taking the effect of the ground motion. Now, this is one unique slide I always say. I have maintained this slide over a period of time. This is one of the oldest picture from IS 189 1984. And just to excite some of my students, good afternoon. Am I audible?
Yes, sir. Please continue.
Okay, there was a power failure. My apologies for the
Yes,
interruption.
sir.
Okay,
Yes,
so I was talking about, yeah, I was talking about the way the
sir.
shear
Please.
forces. I was talking about the way the shear forces are distributed along the height of the structure and how we calculate the base shear distribution along the height of the structure. So I pose this question to some of my structural engineering students as to if you are buying a flat in a tall building, as a structural engineer, where you think you are the most safe and there you would prefer to buy your apartment or your flat, whether it is bottom floors or whether it is top floor or whether it is somewhere in between. And before taking this course on earthquake resistant design of structures, they give some reasons. If it is bottom floor, then it is easier for them to go out of the structure when earthquake happens. Some of them say it is the top one because when the structure collapses, the bottom floors they are hit by the floors above, and therefore they would prefer the top floor, and so on and so forth. However, I'll keep this question open for you to think about, but the answer to this question lies in what you are seeing right now on the screen. The force that we calculate induced because of an earthquake ground motion is basically calculated based on the Newton's second law of motion, which is mass times acceleration is the force. Now here, as we go above, the acceleration increases. If we assume that the weight of the floor remains the same, then obviously as we go above, because the acceleration increases, earthquake induced force increases, and you can see the distribution of that force, which is non-linear. So as we go above, the force increases. And if we cumulatively see the resistance of the columns or the shear walls, means lateral load resisting elements, then they have to carry the shear, and we have the cumulative distribution of the lateral base shear. And we calculate the story shear and how much story shear individual columns in that floor are required to carry out, that we mention in here. So thereby we can very easily see that the bottom columns are required to be designed for higher level of seismic base shear as compared to the top column, whereas the acceleration in the above column, above floors is significantly higher. Now with this physics of the problem in mind, Typically, we work on the coefficient method for designing the earthquake resistant design of structures, and the zone change that happens or the spectrum that changes, that everything is eventually affected in calculation of this VB, which is the design base shear in the structure. For example, now these two plots are given for equivalent static method and response spectrum method in IS 1893 2025 for different load class for site class type. And from that, whatever changes that have happened, it eventually changes the spectral ordinate corresponding to the time period estimated for the structure. From that, the horizontal coefficient of acceleration changes, and thereby VB calculated for the lateral load resisting element changes. So these are the changes in the code which directly affect the design of the structures that you are having. And the last part that I'm going to talk about is, of course, if you are having the response spectrum method, you have load combination, and then the model response combination, because the peaks doesn't occur at the same time. We have to rely on the statistical method of model combination of the responses, and depending on how those model frequencies are separated, we either rely on square root of sum of squares or complete quadratic coefficient approach. Now, in the complete quadratic coefficient approach, uh, the frequencies might be closely spaced as compared to that in the SRSS approach. Now, with this, I would like to give you the concept of the seismic design and why the changes have been made in the overall earthquake resistant design code in the country, and what is the philosophy that the core committee where we have discussed on incorporating some of these changes. One major thing that we have to always bear in mind as compared to mechanical engineers or as compared to uh, aerospace engineers, even as compared to automotive engineers, the number of people affected and the property affected because of the Indian standard codes under civil engineering and particularly against earthquakes is significantly different. In some unfortunate plane crash, the number of people affected would be the number of people on board, which could be somewhere around maybe maximum up to 100, 200. And in automotive crash, typically there are 3, 4 people. If it is a bus, then again about 80 to 100 persons. But if we talk about earthquake resistant codes, the entire country's built infrastructure is based on that. And if during some earthquake, some failure happens, the number of people whose life is at risk is significantly high, which is in few crores, if not more. And therefore, the codes that we develop for earthquake resistant design structures needs to be well designed to ensure that the people's life is not at risk. At the same time, because of the huge construction activity involved in this, there is a lot of money involved in this. We cannot make it unduly uneconomical just by making the column sizes too huge. So we have to meet both the challenges, and therefore our structures and their design is very, very unique. We have to ensure the economy at the same time without compromising with the safety of the people. Therefore, we have this unique challenge in designing the codes. And then I was talking about the latest change in the earthquake resistant design philosophy, which is now based on the return period. As I have explained, the more the return period, there are more chances of major earthquake to happen, and thereby more damage would be caused in the structural elements. And if it is a minor or frequent earthquake, we expect that during the minor earthquakes, no damage should take place in the structure. And likewise, whether we are talking about the main or primary structure, or we are talking about the non-structural elements such as the the HVAC lines, for example, in the structure, air conditioning systems, and these days we also have the LPG supply in our structure through the pipelines. So all those are non-structural. They do not carry the main structural load. And during the earthquake, we would like to see as to which out of them are getting affected and which out of them should not cause any secondary events. Now, the major revision that the new code has seen is in terms of the performance of non-structural elements in structure as well. And now we have a larger spectrum of design levels, and that larger spectrum is given based on category of the structure and what is the return period. I have already explained to you a few slides before that if it is a very, very special structure in zone 6, which is a new zone that has been introduced, a special zone, and the return period based on the probability of occurrence of that event, if it is, let's say, close to 4,975, then the seismic coefficient that we calculate based on the zone is significantly higher as compared to a normal structure in the lowermost zone 2, which has very low risk of even failure as well. We take higher risk of failure because not many people are at risk. So we eventually calculate the risk because we are taking the hazard level as lower in that case. So all these different types of structures are listed in the table given in IS 1893 and categorized into special, critical, important, and normal structures, and with time return period for them. And based on that, we calculate the horizontal acceleration coefficient. So this is one major change that our structure has experienced. Typically, we do not design for the maximum possible earthquake at a particular location. Generally, our structure are designed for lower level of earthquakes. It means uh, when that level, that major level of earthquake takes place, our structures necessarily experience some damage. And because of the damage, it actually helps us to dissipate the earthquake energy in a good manner, and therefore inelastic response becomes the key component in the design of these structures. The behavior of the structure under the earthquake ground motion is significantly different as compared to other events, and typically we make that comparison with the wind loading, for example, because both of them are dynamic in nature and they stay for a certain longer duration, and both of them are cyclic in nature. However, the wind force acting on the structure is non-zero mean loading, though it is oscillatory. Non-zero mean means structure does not oscillate about its mean position. It oscillates about a non-zero mean position because we have some overstatic pressure also acting on the structure because of the air pressure. Whereas in case of earthquakes, it is essentially a zero mean process. The structure to and fro, which is a cyclic loading about its mean position. Now, this fact has been taken into account in the code when typically we recommend some nonlinear dynamic time history analysis. Another very, very significant change that the new code has introduced is giving a lot of inputs related to local geotechnical aspects. And we have learned from past experiences, and one of the most famous example is from Mexico. In 1985, during the Mexico City earthquake, you can see that some of the buildings located at a particular site, they experience a lot of shaking as compared to some other buildings which are just adjacent to it. Uh, though we spend almost 2 to 3 weeks in explaining this to our students, in next 2 to 3 minutes, I will explain as to what has happened here. Mexico City has received this earthquake from its one of the shoreline. The center was several kilometers away. Therefore, the same intensity of earthquake was reached here at the bedrock level. However, earlier there was a big lake here, and over a period of time, when the population increased and there is more demand for the land, there was a land reclamation happened, and the lake started disappearing gradually, and the new structures were built on that. Now, if you see the founding soil, this soil itself responded to the earthquake received at the site, and whereas here it was a natural ground, which is a relatively harder rock than this site, and therefore here soil amplification took place, and the earthquake ground motion experience at the base of the structure was significantly higher than the earthquake ground motion experience here, whereas the source of the earthquakes was exactly same, means same amount of energy was received at both the places, SCT site and UNAM site. But because of the founding rock or founding soil was different, when because of the soil amplification took place, these structures experienced a lot of um, damage or some failures as well. So therefore, our Indian standard IS 1893 new code, it talks about carrying out site-specific analysis, geotechnical investigation, calculating the liquefaction potential, and then designing the structure based on that soil period or based on the flexibility of the soil. This new code of IS 1893 also essentially recommends carrying out soil structure interaction, at least for important structure, to ensure their safety during such earthquake events. In addition, we also need to look into the difference between the mass excited structure or the wind imparted loading on the structure vis-a-vis the ground deformation that takes place underneath the structure. We typically distinguish the displacement control method of the structure and the load control method of analysis or design of the structure. Now, the challenge here is when the ground is moving, there is a displacement and there is no force. So, during the earthquake ground motion, we always say that it is earthquake ground motion and there is no earthquake force. There is an earthquake induced force. Because of the inertial component of the structure or inertia of the structure, some forces which are pseudo in nature, they are induced in the structure. And calculating those forces becomes important under the horizontal action, how the members behave, and then designing those members for that horizontal force. And there comes the challenge. We do not know as to what level of earthquake is going to happen, when it is going to happen, how frequently that level of earthquake is going to happen, which fault will be active, which are not active, and then how the soil will respond. And again, soil has its own variability depending on what layers we have, what kind of rock is there, and therefore quantification of all these parameters which affect finally the response of the structure and the people's life, it becomes very difficult to take into account all these factors in the design, and therefore we have to rely um, fortunately or unfortunately on the probabilistic approaches and take into account the uncertainties in all these parameters. So in some way or the other, the code does take that into account, and we do some quantification, learning lessons from the past experiences from other places and in India as well. And that is how our different coefficients come into picture. For example, earlier our code used to give some different damping coefficient for modifying the seismic coefficient calculator or base shear calculated, but now we are calculating everything based on the 5% damping in the structure. Still, our knowledge in this area is developing gradually over a period of time, and the new knowledge is being now incorporated in the code development. I gave the example of soil structure interaction, for example, and we are also now incorporating the proper inelastic behavior into time history analysis. Thereby we call that as nonlinear time history analysis, where change in the stiffness which directly affects the frequencies, natural frequencies or mode shapes of the structure, quantification of the damping in the structure, and what kind of soil flexibility affect the structure members. These all are now gradually affecting our choice of design of the structure. And now we are gradually improving on our capabilities of carrying out nonlinear dynamic analysis. In the beginning of today's talk, I have mentioned that earlier seismic coefficient method was more prominent, and then response spectrum approach, and very rarely a structural designer used to carry out the time history analysis. Now the things are gradually changing. More emphasis is being given on response spectrum analysis and time history analysis, And for very important structures, nonlinear dynamic time history analysis is now highly recommended. So these are the changes. I will be not surprised that over a period of time, in about a decade or so, time history analysis will become the norm, whereas seismic coefficient method will be used only for very, very small tenements or small buildings, which are really not so important. So I would like to quickly summarize this and switch over to the other aspects of earthquake resistant design of the structures. So essentially, earthquake resistant design philosophy is based on damage. I repeat my sentence, earthquake resistant design of structures is fully dependent on damage because we make best use of the inelasticity or cracking in the structure to dissipate the input earthquake energy, because the universal principle of energy remains valid. Of course, it cannot be violated, that the total energy always remains same. It only changes from one form to the other. So therefore, when during the earthquake ground motion ground shakes, that energy is input to the structure, and it has to be diverted to some specific locations which we allow them to get damaged, and then we may repair or we may replace them as we go along. So that energy input to the structure from that earthquake ground motion needs to be looked into. There are different ways to take care of that input energy to the structure, but what we are talking about as per IS 1893 is we take that into account based on the inelastic response of the structure, which we ensure by having the response reduction factor incorporated in our design. Now, when we design our structure and what kind of failure we allow, which member should fail, that also needs to be decided. For example, if we identify one member of the structure to take the entire earthquake energy and thereby rest of the members are not failing, that member should be such that its collapse should not lead to progressive collapse of the whole structure. Obviously, it cannot be, for example, a column at the bottom story. You have seen already the distribution of the shear force. The shear force, the lateral shear is much highest at the bottommost story. So thereby we decide as to which member or which members in the structure would first receive the inelastic force level of response. Again, if that member is column, then larger area will be affected. If that member is a horizontal member like a beam, then lesser amount of volume in the structure would be affected. Even the failure also we would like to govern as to which kind of failure should happen. For example, we do not want bond failure to happen. We do not want shear failure to happen. The reason being that they are brittle in nature. We do not get adequate time before the failure occurs. Whereas if it is a flexural failure, it is a ductile in nature, and therefore we get adequate warning before the failure occurs. So we talk about whether it is a sudden failure or brittle failure, or whether it is a gradual failure where we do get lot of warning. We also talk about which member to fail, means where the plastic hinge will develop. Plastic hinge essentially means that structure has gone into inelasticity. So this way we decide the hierarchy of failure. That hierarchy of failure depends on what strength these different members have, and accordingly we decide as to what we do allow to allow failing and what we don't allow at all. For example, we may allow slabs or beams to fail as compared to columns. We allow column to fail then foundation. We don't want foundation to fail before columns fail. And obviously at the foundation level we don't want any liquefaction to happen and the whole structure getting collapsed. We do not want that. So that is the hierarchy in case of, for example, multi-story reinforced concrete building. And in terms of brittle and gradual failure, we decide whether the yielding in bending occurs first or whether it is a local buckling that occurs first. Before this class, you must have heard this strong column, weak beam, or weak column, strong beam kind of a concept earlier. Though sometimes it is not fully understood as to why we say so, but just now whatever I have discussed, that might have made it clear to you that if our beams are stronger than columns, once the column fail, there is a likelihood of the entire structure to fail. But if it is a strong column, their capacities are higher than the beams, then even if some local beam failure occurs, the columns still stand perfectly all right, and there is no serious consequences of earthquake to happen. This essentially is what I have talked in the previous slide, that we decide the sequence of failure in terms of where the plastic hinges are getting developed. Obviously, when it is a weak beam strong column concept, the plastic hinges are first developed in the beams and then in the columns. As against this, here in this case, when the beams are stronger than the columns, then the plastic hinges are first developed in the columns and the entire structure is likely to fail. This concept can be very easily explained with respect to a chain which might be pulled from both sides, and if all the links design is considered to be the same, the failure may happen theoretically in each link, which we do not want. These links you can see as the columns in the structure, and this force that is applied is the force induced because of earthquake. Now instead of that, we keep all the design and material geometry of all the links same except one link, and that link, let us say we make out of rubber, which has larger flexibility and energy absorption capacity. When the force is applied as compared to the other links, this link of rubber displaces a lot. There is increased amount of energy dissipated or work done in that elongation of that rubber, and even if it fails, we can replace that with another link, but we have concentrated that failure at one link which is pre-designated, whereas we know that other links are not going to fail. Now you can compare that with the building where one column or few columns identified are allowed to fail, and their failure has some redundant effect on the structure, so that there are some alternate paths already available, and their failure does not cause the entire collapse of the structure. So that is the basic uh, design philosophy which comes under the capacity design concept. And then where the first hinges should occur and what should be the sequence of occurrence of the hinges. So these yellow colors are the hinges. If you design your structure for larger deformability, it signifies a higher level of ductility, and thereby large amount of energy is under this curve, which is the area under this curve is the energy that the structure has capacity to dissipate or absorb. If we have large number of hinges to be developed before the complete collapse occurs, it is the best design, whereas only few or one or two hinges itself causes the complete failure of the structure. The area under the curve is very small and we experience essentially a brittle failure. So that is the essence behind capacity design concept. Though as of now we have not fully incorporated capacity design concept in our code, but over a period of time it will be incorporated, and now we have indirectly incorporated the way we design our structures currently from the present concepts, that typically the collapse of the structure is avoided completely, whereas the progressive failure should happen in such a manner that lesser amount of volume of the structure is affected because of that. This concept has been arrived from the way the structural frame behave under the vertical load and the horizontal earthquake load, and what kind of um, response is shown by the beams and columns, and what kind of bending moments and shear forces developed in them. Obviously, we understand that in the rigidly jointed beam column connections, the moments at the ends, they are equal in column and the beam. And thereby, if we talk about the hinge development, if the hinge is to develop in the beam, obviously hinge must get developed in the column as well, because they may have the similar moment. And thereby, in order to push the hinge in the beam rather than in the column, the earlier concept which I have talked about of strong column weak beam comes to help. In that case, the weak beam will have the hinge developed first, and then the what has happened? Is my screen visible? Doesn't look like.
Yes, sir. No, sir. No, sir. Not seen.
Yeah. I'll share it again.
Yes.
Yeah, I was here. Okay. So thereby these strong column and weak beam concept help us to ensure that the hinge is developing in the column first, in the beam first, than the columns, and at the top stories typically the hinges are developed first. There is a learning lesson to us from the unfortunate Bhuj earthquake in 2001, that the bottom columns have completely failed because of the higher shear forces, whereas the top columns they have received no damage as such. So this now is already incorporated in our codes, and I have talked about the failure modes, in what sequence we would like the failure to happen, and some of the failures we do not even want them to happen, and thereby everything finally boils down to ductile design, and thereby we do not want any compression failure to happen. We want the reinforcement to yield first, and we do not want the shear or bond failure to happen. We want the beams to fail rather than columns to fail. So everything is revolving around the failure behavior or failure pattern of the structure, and code has given some mandate to design. And then in addition to IS 1893, we also have IS 13920, which talks about the ductile design code. Now, this makes us to firmly believe as to why it is so important to have the ductile design of particularly the reinforced concrete structures. Of course, in case of steel structures, we do get good amount of material ductility in our structure. So ductility we typically define in terms of how much is the area under the load deflection curve. Here the load we are designated as the horizontal load acting on the structure, horizontal load induced on the structure during the earthquake, and the overall total deformation at the end. Typically when I explain this to my students, I want them to see this figure, the building figure, as 90-degree clockwise direction rotation. So it looks like a cantilever beam, and that cantilever beam is subjected to some distributed load, which I have shown you from a old IS 1893, and that cantilever is subjected to that distributed load and how bending moments and shear forces are developed in that. Of course, that load acting on it is dynamic in nature because of the earthquake and because of the inertia of the structure. There is a time history uh, of the earthquake induced loading acting on the structure. Now, in order for the structure to dissipate larger amount of energy, we have to see what are the means available for us, so that instead of getting the poor deformability of the structure, we get a very good deformability and have a larger energy dissipation capacity ensured in the structure. And therefore, we have the hinges developed in a sequential manner, typically in the beams to start with, and at the top typically, and even if they are developed in the bottom stories in the columns, it should not lead to disproportionate or non-proportional collapse in the structure. So this slide summarizes when I was talking about the hinge development in the strong column weak beam concept. In addition to that, wherever there are sudden change in the stiffness in the structure, typically hinges are developed there because there is sudden change in the bending moment and higher concentration of the forces occur. And therefore, code also mandates that what could be the horizontal and vertical irregularities possible in the structure. If there is torsional coupling in the plan, then again it induces higher forces to some of the columns which are away from the center of rotation, and thereby the code also gives that how much should be the story stiffness variation along the height of the building. But the most important concept in this case is to ensure the ductile failure and ensure the larger capacity of reinforced concrete columns. We understand that if we give the confinement to concrete, it has larger capacity to carry the load, but in addition to that, it also has larger area under the curve. It means it becomes more ductile than the unconfined concrete. You can see in this particular plot for concrete that if there is no confinement to the concrete, it fails like this. So you can see the area under the red color curve would be very small. And if we confine the concrete, then the area under the curve is quite larger. And then how do we ensure that our concrete is confined? And that happens because of the transverse reinforcement. Transverse reinforcement in case of beams is the shear reinforcement, shear stirrups, and the transverse reinforcement for confinement of columns is basically the lateral ties. If they provide adequate level of confinement, then the same concrete exhibits larger energy dissipation capability, and thereby we get a very good ductile behavior of reinforced concrete structure overall. These are some of the examples I have taken from the Polly and Priestley's book. Therefore, the figure quality may not be as good, but it clearly highlights how confinement becomes important. Now, this is particularly in case of the column section, that if we have the lateral ties very nearly placed, if their spacing is lower, then majority of the column cross section has the confinement received to the concrete, and thereby the energy dissipation capacity is significantly higher in columns. Now, similar we need to ensure in case of beams as well, where in the tension zone and compression zone, we have the steel reinforcement and concrete to take the tensile and compressive stresses respectively. But particularly when we talk about the compressive zone, there if we have the confinement given through the stirrups, then the ductility we achieved is significantly higher. So we look into what is the failure behavior of a particular continuous beam, which are very common commonplace in the structures where the moments reach higher. And obviously, as I have said earlier, earthquake induces to and fro load, means cyclic loading. And because of the cyclic loading, there is a reversal of stresses. And because of the reversal of stresses, we need to also ensure that the part of the member which is under compression is likely to go under tension in the next loading cycle, and part of the member which is in the tension may go in the compression. And in that cyclic loading condition, we have to ensure that the area under the load deflation curve is significantly higher. That we provide by providing, that we ensure by providing extra bars at those locations where the bending moments would be higher. So these are the challenges in the design first. But then there are construction challenges as well as to how we need to put them across. So there are some guidelines available on this in some codes as to how we ensure this kind of confinement and how we calculate those additional reinforcement requirements in the structure, both in the longitudinal and transverse direction. And the provisions given in IS 1893 essentially takes care of the confinement provided to the concrete as much as possible in the cyclic loading condition, wherever the bending moments uh, are likely to go significantly higher. So these are some of the provisions given in 13920, which is also again in the revision stage, where we should allow the lap typically wherever the bending moments are not likely to be higher, which are the locations near the point of contraflexure. So there we may allow lap, and at one location not more than 50 bars we have allowed lapping, and when the lapping happens we provide closer spacing of the transverse reinforcement. Also, what should be the anchoring longitudinal bars, or what kind of development lengths we need to provide, again which depends particularly on which beam column location that we are talking about, and we need to at least provide 50 times diameter of the bar in that location. Again, as compared to the non-reinforced beam, the behavior of the reinforced beam is very well known to us, but behavior of the beam with confined reinforcement, confinement to the concrete with the higher confinement reinforcement given, is further eye opener for us to see as to how much enormous ductility it provides in the structure. Depending on that cyclic loading that we have, we evaluate the locations where we need a particular type of energy dissipation. However, in order that the concrete should provide, concrete should be provided with the confinement through the transverse reinforcement, we have
त्यांना बारामतीत हे नाही त्या माळेगावला राहिले म्हणलं मला सध्या
these lateral ties or transverse reinforcement provided with these loop reinforcement. So theoretically, many of you being the faculty members would be aware that we theoretically we can provide a U type of stirrup. We don't have to close it because the shear strength requirement is in the vertical legs. So when we calculate the SV for the given amount of shear force, we calculate what is the area requirement based on how many legs of the stirrups we have. We do not take into account this top element and bottom element. However, though theoretically for a given type of flexural loading it would work very well, but it does not give any confinement. So that extension of that leads to providing such kind of a loop that it will not open up during an earthquake to and fro shaking or cyclic loading of the earthquake. I can again spend almost about a month or so explaining the mechanics behind this, so that you need to it needs to be born in your mind that this is one of the very important concept in ductile design of reinforced concrete member, which governs the hinge formation and confinement given to the reinforced concrete members. So some of the next slides essentially talk about how the ductile detailing of the reinforced concrete members mentioned in IS 13920 helps in having a ductile failure in the structure as against the brittle failure. In particular, I would like to bring your attention towards some failure happens in the school buildings, which we do not want any failure to happen at, have been because of the short column effect. And that short column effect essentially was pertaining to development of some irregularities as well as having no adequate confinement. And wherever there was adequate confinement, the behavior was extremely ductile. So this is the mechanics behind the ductile failure of the compression member under the different spacing and diameter of the transverse reinforcement. So I'm skipping some of this slide. It gives you more details about the ductile detailing of beams and columns and shear wall. I would like to now almost conclude my presentation. I have only probably 3 minutes left. So I would like to summarize a few of the prominent things in this. That what I have talked about mainly are the 4 virtues of design of earthquake resistant structures, and I categorize them into 2 parts. One that is seen by the structural engineers and other that is taught by the architects. I deliberately did not highlight too much on the architects, though next few slides I will talk about configuration. But my focus has been more on the structural engineers. So strength, stiffness, ductility is something that we need to worry about. Out of that, I have again talked mainly about the ductility to start with, but I would like to further highlight about the importance of strength and stiffness. Indirectly, we talked about it when I was speaking about the response reduction factor. But what we have to keep in mind that depending on which kind of material and how they are put in the structure and how we calculate the response reduction factor, the inelastic response of the structure completely changes. I have already explained to you the concept behind the response reduction factor and how the ductility, redundancy, and overstrengths are taken into account. But what is most important in this case, which I am yet to discuss, is what is the force deformation behavior of a particular member, and in this case, the lateral load resisting element, which is the columns. Now, the column may have the strength deterioration or it may have the stiffness deterioration. You can see here in the left-hand side curve, over the next cycle of next cycle of earthquake loading, there is a reduction of peaks here, whereas there is more or less constant slope of this line. Obviously, slope of load deflection is the stiffness. So there is hardly any stiffness degradation, but there is significant strength degradation. Whereas in the right hand side plot, you can see that typically the strength level, which is the H part, it is more or less constant here. However, if you see the stiffness, which is the slope of this line, if you join these peaks here, you get the slope. the slope in the next cycle has started going down. Slope is going down, it means K is reducing. K is reducing means stiffness degradation happens. Now, in a real life reinforced concrete column, both of them happen simultaneously. So if you see under the earthquake loading, which is earthquake induced loading, which is cyclic in nature, typically the force deformation loop that we see has both strength and stiffness degradation. So you can see here that strength and stiffness degradation curve. And if we connect the peaks of these force levels, then we get the red color curve. And then we have some possibilities of whatever lateral load resisting elements that we have, whether we get this kind of S-shaped curve or we get this kind of S-shaped curve. If our structure is showing this kind of S-shaped curve, it is a poorly designed structure, and if we get this kind of structure, it is a well-designed structure. Particularly, you can see there is a significant pinching effect here. The area enclosed is lesser as compared to, in this case, area enclosed is more. It means larger amount of energy is being dissipated, which again can be achieved by virtue of providing ductile detailing in the structure. So a lot of discussion is required on this ductility and how we evaluate it, how we quantify it. But then also we need to see at which location we achieve this ductility from. For example, there is a overall structural ductility and right up to the section level ductility, cross section of beams and columns. There could be member level ductility, which is beams and columns at overall member level. Each story will also have certain ductility. Some stories will be more ductile than the other. So likewise, the locations of the ductility or where we are ensuring those ductility from may also be significantly different. We may design the structure depending on which members we would like to yield, which members we would like them to fail and experience more damage. So that discussion we carry out that discussion based on the load versus displacement response right from the section level, member level, story level up to the overall structural level. And based on that philosophy, we calculate the response reduction factor. In that, typically there is some detailing required as to how we evaluate the response reduction factors, and they are affected by material parameters, how many redundant paths or alternate paths are available, what kind of material factor, load factors are being used as such. And finally, we evaluate the response reduction factor. So the table given in IS 1893 for response reduction factor is based on all these different factors taken into account, and some of the examples I have already given to you. The other ones are related to, as I have said, out of the four virtues, we talked about the stiffness, strength and stiffness. I have talked about strength and stiffness, but stiffness also affects the frequency or time period of the structure. And again, based on the spectrum that we are choosing, the design would be affected as to what is the stiffness degradation as we go along. And the last one is that by the configuration, which is a geometric part typically taken care by architects. And typically they have to worry about the geometry of the structure and its size, shape, and how the elements are distributed along it. There are some provisions given in IS 1893 that what kind of irregularity the structure may have and what are the limits given to that. I do not want to spend a lot of time on that because typically architects they are more concerned with that, and when structural engineers design the structure, they have to ensure when the members are provided, the different irregularities of the building are avoided and made within the prescribed limits in the code. And these are the figures directly taken from IS 1893, which talks about the what are the torsional irregularities depending on how the lateral load resisting elements have been distributed, if there are certain heavy masses, and how the plan configuration of the structure is, and how the different elements are distributed in the plan of the structure and in the elevation of the structure, which causes some vertical irregularity, and how the shear, how the resistance, center of resistance changes depending on the orientation of the lateral load resisting elements. And then the stiffness irregularities in the vertical direction to avoid the soft story effect. Some provisions are given in the code. Likewise, typically based on the configuration, we also achieve earthquake resistance of the structure. So I'm skipping some of these slides which are directly available in the IS 1893 as the clauses. So in summary, I'm quoting here Henry Degenkolb from USA. And in nutshell, what he said is if there is a poorly configured building, then basically it will have a very severe response. And on the other hand, if it is a well-designed building, obviously its performance will be good. But on the other hand, if it is a poorly configured building, means architect does a poor job, then even if structural engineer does a good job, it has more vulnerability, seismic vulnerability, as against a very well configured building in terms of its geometry or shape and size. Even if it is relatively poorly designed, its still performance would be much better comparatively to the other one. So this, you might see that this is a completely text-heavy slide, probably the only slide that you have seen so far, which is so text-heavy, and even the font size is also smaller. But what my intention behind this is to summarize whatever I have talked about in today's about 1.5 hours. I have summarized everything here, whatever I have discussed as to how the new code 1893 has seen some of these changes based on the data available to us, the probabilistic seismic assessment, the zoning that we have done, and then how the response spectrums have changed and how the local geotechnical effects are now being taken into account in the design, how we are also paying attention to the non-structural elements in the structure. So all that I have summarized in my today's presentation. So many of these things are taken from some of these references. Also, I express my sincere gratitude to Professor C.V.R. Murthy, who has contributed significantly to this, Professor Durgesh Rai from IIT Kanpur. They have also contributed a lot. And before I conclude, once again, I express my gratefulness to Professor Kate to give me an opportunity to have some dialogue with you all. And with that, I open the forum for questions if you have any. Thank you very much, one and all, for sparing your time and listening to me patiently.
Thank you, sir. Thank you. Thank you, sir. Yes, questions from any audience?
No questions means probably I have done a very good job.
No, sir. No, sir. Yes, Garg, sir, any question? Okay, please ask any question. Okay.
Yeah, we should ask, the audience should ask questions.
Yes, sir.
Yeah. Please do not hesitate in asking questions, whatever that you may have.
Sir, I have one question.
Sure, sir.
There are many changes in IS code
Yes.
1893.
Yes, sir.
So, what major changes that highlighted?
So the major, the most prominent change is the zoning map has changed.
Yes.
And earlier it was based on the deterministic hazard assessment. Now it is probabilistic hazard assessment. So almost invariably, most of our bigger cities are affected in terms of for what zone factor they are being designed. So that is one major change which has happened in this version.
Okay. Okay.
Yeah.
So it is specially recommended for bridge or high-rise structure or any other high-rise building.
That again depends on the importance of the structure. Earlier, this return period concept was not there in the design, but now return period is another very important concept introduced in the new code. Now, if it is a bridge, it is an important structure. If it is a, let's say, 1-story, 2-story residential structure, it is not an important structure. So depending on that, we consider whether it is a normal routine structure or it is a very, very special or important. According to that, the seismic zone coefficients are changing.
According to the older structures, is there any risk to from earthquake in India, like bridges, high-rise buildings?
Yeah, it's a very pertinent question in this case. And people are saying that overnight the structure which was safe yesterday has become unsafe today. How is that possible? So
Okay.
obviously it doesn't happen that way. The structure which has a certain risk yesterday has the same risk today. Only our evaluation of it has now been different, and our perceived risk to that structure, if it has changed, that the structure is at more risk, then we have to take some intervention of retrofitting. If we still feel that we are okay to take that much of risk, and particularly our insurers, means insurance companies allow us doing so, we don't have to carry out any retrofitting even if there is change in the code. Obviously, a building which is or a bridge which was code compliant yesterday, means when the previous code was in force, suddenly cannot become non-code compliant in today's date just because the code has changed. Our perceived understanding of how much risk has been posed to that bridge or that building has changed, and based on that changed perspective, whether or not we require some structural intervention, that is a decision we have to make based on how much risk we would like to take.
Okay. You
So,
mentioned some example also, Mexico City in 85.
right, absolutely.
And yes, city side, soft soil and basalt rock, maybe something. Yes, yes. Okay, one last question is, there is on last day, that is 9th January 2026, I think 11 shocks absorbed by Gujarat. So is there any history or that any kind of generator?
Yes. So, as I have said in my talk also, now we have a capability of recording several earthquakes, and that too in a broader range. Now, these earthquakes were also recorded, those time histories are available, and over a period of time, they will become available for the structural engineers to use them, particularly those which are in that region.
Okay, sir. Okay.
Yeah.
Nice interaction.
Yeah. Thank you so much, sir.
Yes, any other from audience? If no questions, so we can conclude.
Sir, good afternoon, sir.
Good afternoon.
Myself, Dr. Kaple, from JSP Nare Technical Campus, Pune.
Yeah.
So presentation was very nice, sir. Very briefly, we have explained everything. Just I would like to uh, uh, related to as per your topic, challenges you have mentioned. Right. So as a design engineer, what kind of challenges we need to focus in our mind?
Right. So while I was responding to Dr. Kate, I have also mentioned about retrofitting. I have also mentioned about how the change in the code had changed the whole perspective. But as a structural designer, you will be posed these questions by some developers or some residents. So there you need to respond it in the same manner. That basically overnight things doesn't change like this. The code has improved quite significantly, and thereby we have a better understanding of the behavior of the structure, how it is to be designed, and then what is the risk associated with that. That is one part of the story which I have responded in response to the question asked by Dr. Karte. However, if we have a new structure referred to us for design in today's date, then as a structural designer, you have to make several decisions. And I'll give you one example. From that return period table, when you have to calculate the zone factor, what decision you need to take based on whether it is a commercial building or residential building, how high or tall that building is, which location it is dependent on. All this are the decision that you have to take, and that is where you may face as to how do I categorize that building, whether it is very important building or not an important building, for example. So that has direct effect on how you are going to design that building. That is one challenge, for example. The other challenge could be the development of site-specific response spectrum and then spectrum compatible or quick time histories. In order to develop site-specific response spectrum, you need a lot of geotechnical data available to you. Whether that geotechnical data is readily available to you or not, again becomes another bottleneck in developing the earthquake resistant infrastructure. That becomes another challenge, particularly to the practicing structural engineer. The practicing structural engineer may have to rely significantly on the geotechnical engineer to carry out the site-specific investigation and give you that input. So these are challenges in the designing real-life structures, particularly with the change in the codal provisions. Having said this, there are still solutions available for this. Our earlier practice of designing the structures by using seismic coefficient methods, of course, they are still applicable. And from these new tables, we can still select the earlier values and go ahead and design the structure. Now we also are able to quantify the risk associated with that. So these are in nutshell what challenges are. During my
Yes.
presentation in the slides, I have directly or indirectly highlighted the challenges associated with it.
Yes, sir.
Yeah.
Thank you, sir. Thank you so much.
नाव लिहा की तुमचं
Yes, any other questions? Okay, so thank you, Matsagar sir, for delivering today's wonderful session regarding earthquake resistant structures and their challenges. So this session is very valuable and fruitful to all our participants. So once again, I thank you, Matsagar sir, and thank you all participants. Next session will be start within 2 to 3 minutes. Thank you, sir.
Thank you very much.
Wait, sir. All participants, please on your video. We have to take a photograph. Yes. Yes. Just a minute. Some people are on their video. Okay. Yes. Okay. Just a minute.
Yeah.
Yes. Okay. Thank you, sir. Thank you.
Okay. Thank you very much, everyone.
Yes, sir. Thank you. So stay online. Hello. Have you seen my screen?
Yes, sir.
Yes, sir.
Yes, sir.
Let's see. Let's see. There is a reflective journal regarding this Atal FDP program. So all the participants, you have to write this or print this, take this print of particular reflection journal. And from this, your name, institute name, FDP title, dates, and submission date. Also, you can write key learnings from this FDP. Learning outcome 1, learning outcome 2, and learning outcome 3. So you have to write there from out of all 13 sessions, what you have to learn. So this key learning outcomes you have to write here, okay? And then second point is key lessons, concept and ideas for your implementation. So list of any three ideas or concept that will implement in your teaching and research. So concept one, idea one, concept idea two, and concept idea three. And third point is that implementation plan, provide implementation plan for your three key concepts. Implementation plan number 1, plan number 2, and plan number 3. So all participants, you have to submit this. And lastly, participants should write their roll number or ID. We will provide
मैम
you.
जब वो आएगा तब दे पाएंगे हम। हाँ, स्टूडेंट को ही देंगे, इसके बिना किसी को नहीं देते हम जी। हाँ
Yes. अरे mute yourself. Please, once again, at the end, you have to participant write their roll number, submission date, okay, and submit me on my mail ID. I will provide you mail ID personally second, not this given on voucher. So this will be all should be take print and submit by participants on soft copy to my mail till the Monday morning, that is 12 January 2026. Okay, so it is very important regarding, so implementation plan, key lessons, and learning outcomes you have to write. Okay, our session will start.
सर ये फॉर्मेट शेयर करेंगे आप व्हाट्सएप पे?
यस सर व्हाट्सएप पे मैं शेयर करूंगा और आपको उसको लिख के या टाइप करके भेजना है मुझे, जो उसका रोल नंबर मैं आपको भेज दूंगा। वो रोल नंबर में मैं आपको बना के भेज दूंगा आज शाम या कल सुबह तक, और मंडे मॉर्निंग तक आप मुझे सब मेल पे डाल दीजिए। ओके ओके, थैंक यू। आवर सेकंड सेशन स्टार्ट विल विदिन 2 to 3 minutes. Mike sir, hello.
Yes, sir.
Yes, you are joined.
Can I start?
Wait, sir, wait. If possible, share your screen, sir.
Sir, it is visible?
Yes, sir. Yes, visible.
Yes, sir. Good afternoon to all.
Yes, good afternoon, sir. Please.
Sir, can I start? Yeah, wait some time.
Wait.
Please speak loudly. I think the voice is
Today's
low. Yeah,
today's session.
Okay, I am audible properly, sir?
Yes, sir.
Okay.
Today's second session, transforming construction, traditional methods and 3D printing.
Hello, sir. Bobde, sir.
Hello.
Please, sir. Please, actually, in my first session, I'm just there is a part that is concepts we are discussed. Now, practical applications of sensor we are going to do.
Okay.
Let's just go.
Okay.
Explain the topic.
Sir, this is the part of that session.
Yeah, yes, sir.
Transforming construction.
Yeah.
Okay, sir. Okay, sir. Please continue. Bobde sir, please continue.
Okay. Today's speaker, Dr. Chitranjana Naik, sir, Head, Dean Autonomy, Associate Professor, Department of Civil Engineering, VP KBIT, Baramati. Sir was received research grant under the Savitribai Phule Pune University, Science and Engineering Research Board, Government of India, and VH Khatri Construction Private Limited. Sir have achieved remarkable achievement. 7 sponsor project undertaken and grant received, 8 patents and copyright, 61 research paper published in international journals, 18 paper presented, published in international conferences, 16 papers presented, published in national conferences, 27 STTP workshop organized or attended, 6 workshop conference organized, 9 national international program courses completed, 20 keynote speakers, invite talks, session chairman, resource persons, and 28 book authored and chapter edited in books. Sir has key contribution to NBA and NAT accreditation activities. Over to you, Mike, sir.
Thank you, sir, for your again nice instruction. Nice introduction. Thank you once again to Dr. Kate, Dr. Bobde sir, FDP coordinator and management and principal of SBM College of Engineering, Malegaon. This is my second session, which is in first session we have see that the structural health monitoring, that is what are the structural health monitoring, basically we discussed about that. Because of some changes in the speaker, then Dr. Kate is request me to do the second session. So I'll just told that we have only discussed the concept and structural health monitoring parts, but we are not seeing the theory and concept applications, practical applications of that. What kind of practical application I do in that topic. So I am more flexible to do that. So he is agreed and just we change the topic and that are done. So here we just 1 minute. Before we are going to see the applications and concepts of all these things of rigidity sensors, that is that piezoelectrical sensors, we have need to know, basically we have applied these sensors to every part of the structures, every type of the structures also, but generally we have thinking about the concrete. So what is the concrete? That is, if you see here, that is the total concrete having 9 to 15% of cement, then 15 to 16% of water. This is the paste of the cement and water. Okay. Then if you go to the mortar, then that is that paste, the cement paste, that is water and cement become a paste. And if you go to the mortar, then we need to find out the fine aggregate into that. Add to the fine aggregate to that paste. Then if you go to the concrete, that is mortar plus coarse aggregate. That means that paste means cement, water, then it is fine aggregate. Then we go to add the coarse aggregates, then it is a concrete. Now this concrete is depend for gaining of the strength, as we all know. For gaining of that strength, we need know the concrete properties, that is hydration process. This is the something that compound of that how the strength is gaining. Why I tell that? Because what are the project we are practical application to the structure, then this kind of we apply the concrete, then this is the basic of something. Then this is the hydration mechanism of a concrete. That what are the paste, cement, water aggregate and fine aggregate. We have there is a hydration process, and because of that hydration process, we getting the strength of that in that structure. Then this is the curing development of a concrete. If you see here, this is that day in day, that is first day, third day, 7 and continuous, the strength gain of a concrete. This is the development of concrete because of the curing. Then this is the morphology of a hydration production in 7 days. If you see, these are the hydration process. Why I am telling about, because of that I am talking about the sensor, but I am same times I am going to see what are the hydration process, because we are now going to apply and see the applications of PJT patches on concrete structure. This is cube, slab, and beam. Before that, we must know about that the how the hydration process of cement is take place and how the sensor is going to working. So this is as we know, that is what is PJT. The PJT patches is nothing but it is a if you see here, just before going to details in the PJT and the sensor, we must know the what are the sensors, and for that I am just find on videos, interesting video, the what is the sensors is like that. Okay, just Kate sir, Kate sir, Dr. Kate.
Yes, sir. Yes, sir.
Can you stop sharing your screen?
अच्छा, मुझे स्टॉप करना पड़ेगा क्या? मैं आप शेयर कर सकते हैं?
I think there is something.
I have make you to co-host, so you can share your screen. Images part 2. अगर मैं भी स्टॉप करूंगा तो कुछ फर्क नहीं पड़ेगा सर, आप शेयर कर सकते हैं.
Just 1 minute, sir.
यस सर. हाँ, आ गए सर, स्क्रीन आ गया.
Okay, just watch this video.
वीडियो इज नॉट सीन सर.
What, sir?
वीडियो नहीं दिख रहा है.
वीडियो नहीं दिख रहा है सर.
Just 1 minute.
लॅपटॉपचा असू द्या सर. लॅपटॉप असू. इन केस कशाला लागलं. हा.
Okay, see here, here is a low frequency PJT patch is there. This is low frequency PJT patch. जैसे वो बोल रहे कि PJT patches मार खाने के लिए है, तो this just like what is that? If you put the pressure on that PJT patch, then it will be convert the electrical. It is create the electrical energy, that mechanical energy, which is going to convert into the electrical energy, and again this electrical energy will be converted to mechanical energy and get the output. So this sensor is nothing but it is acting as an actuator and a actuator and a vibrator, that both can we do this in sensor type. This is one of the low frequency sensor what is we are seen here, but there is a lot of high sensing technology sensors also there. Just next video which is going to teach see how we are going to generate the electric signals from the
टाइमिंग 19 करूंगा सर. 7:15 करू. झालं. क्वेश्चनर सबमिटेड सक्सेसफुल. आता तुमच्या लॉगिन मध्ये दिसतंय का बघायचं. चालतंय येत.
This is one of the topical video which is this is PJT sensor and which is going to generate the electric from that PJT sensor. Just see here, it is the PJT sensor which are in that video we are tapping on that, and it is create the sensor and the electric signals, and these signals which is when we are going to pressure put the pressure on that sensor, it will create the electric signals.
Sir, please full screen.
Yes sir.
full screen कीजिए. Yes.
Just here, see here that the PJT patches, when we apply the forces on that, then it will be create the electric signals. Again, same time, if you look, if you put in the structure, it can be converted the mechanical energy to the electrical energy. Okay. Okay, now we are going to our what is PJT, and if you see here, this is the principle, physical principle of PJT. If you see here, the mechanical stress, when we apply that mechanical stress, it will be going to convert this mechanical stress to electrical charges, and again this electrical field is going to mechanical strain. If you putting in that PJT patches on the structure, then when we are going to apply, or when we are going to when the structure is going to under stress, then the mechanical stress is directly converted to electrical energy, and this electrical field again go to the mechanical. Then we able to know what are the physical properties of that, what are the vibration, or what are the others are coming on that. This is the equation which is NDT technique, which is PJT sensor is working. This is the basic principle of that. These are the equation and how these patches are working, and what are the mechanical impedance and all this. This is the mechanical impedance technique which is used to measure the electrical convert the signals. So these are the instruments basically we are going to use in a sensor technology, that is digital oscilloscope, and this is one of the LCR meter, and these are the patches, PJT patches. Till date we are using this equipment for the, it is sufficient to, I think suppose we are going to conduct an experiment to using PJT sensor, this is sufficient instrument, or it is not so much costly actually. Then this is the how this PJ electrical patches as working. If you see here, there is a mechanical energy supplied to that structure, then it is converted to the electrical energy store, then electric energy supplied to mechanical deformation. When you get the deformation in the structure, then we get the from the, if the mechanical energy is converted to the electrical energy, and electrical energy going to check the deformation, mechanical deformation, then we are going to find out the, after finding out that deformation, then we can find out the condition of the structure. Then it is here, this is, there are two things which is applied into the structure, that is conductance and susceptance. This conductance is the real part, dispatch electrical energy, and this acceptance is called as store the electrical energy. This is the more there is basic, which is going to, these are the thing we are going to study. So here this is one of the structure where the PJT patches is applied here. This is total structure and this is the graph. When the vibrations coming from various sources, these PJT patches can receive the signal and it will be converted to the energy. So this is the electric impedance technique. There are a lot of techniques which is used to find out the total response of the structure. There is a one technique is called as electromechanical impedance, that is EMI techniques. This EMI techniques, if you see here, this is total formula for finding out the vibrations and all this. This is called as EMI technique, that is electric impedance technique. So now these are the formula, and we are now going to apply these types of concept to various types of practical application, to various types of this technique we are going to apply to the various types of structures. Before we are going to see what are the types of applications we have applied using this concept. Now, what is the sensor technology is doing for the civil work? Just to see this video.
Infrastructure is crucial for our daily lives and our economy. These multi-trillion investments are exposed to significant risk through aging, high utilization, and stressful environmental conditions.
Our sensor solution monitors the most critical factors for the structure and health, as they are commotion, humidity, and temperatures. Technology as such is completely unique because the sensors need.
So sensor is not only take the deformation only, it will be act as a temperature. If various temperature can sense, then it can be sense as a stress and all this, and corrosion also.
Batteries and no cables. It can last for 30, 40, 50 years or longer inside the concrete structure.
Our solutions have been implemented in a variety of situations, including bridges, tunnels, and public carpets. One of our most recent bridges is the Zurbrücke in Koblenz, Germany. During a refurbishment in 2022, 28 corrosion and humidity sensors were retrofitted in a variety of accessible locations, which are particularly critical and exposed to significant corrosion risks. The sensors are wirelessly connected to our self-developed gateways without breaking and therefore damaging the concrete surface. The gateways can be powered by an existing power supply, batteries, or with solar panels.
Our customer profits by the early identification of upcoming issues, so we can react in place and in time, radically reduce the amount of damage and the resulting repair costs. But not only the repair costs as such can be reduced, even the inspection efforts can be optimized because the system works completely online and all the information are digitalized, so there is no need to get on site to read out the sensor information.
Our solution delivers high sustainability benefits by significantly reducing inspection and maintenance visits, along with the associated costs. More importantly, repair and refurbishment costs are either avoided in their entirety or substantially reduced, and as a result, the lifespan is considerably extended. We provide unique solutions to effectively and efficiently extend the life of your infrastructure and system, minimizing costs associated with inspection and maintenance, as well as maximizing safety and sustainability. For further information, please visit us at infrasalute.com.
Okay, so these are the important what are used in the which is used the sensing technology in various field. So here, this is the first experimental setup. What are we are doing in our already done in our research work. We are applied these PJT patches and calculate the concrete strength over the time. What is the over the time? This is for 1 day period, second, third, because this sensor is not only work on the deformation, it is also work as the sensing, that is temperature. How the temperature is, as you know, as first what I am tell before my sometimes ago few slides before, that is the mechanism hydration process of the cement. The hydration process of cement is working on the temperature. So because of that temperature, how the cube strength is gaining, we are measuring using that PJT patches. This is our first applications to the concrete cubes. If you just see here, this is our digital oscilloscope. This is one LCR meter, and this is the cube. Or here, this patches, you can see here, this is low frequency patches. This is only in market, this is available for 10 rupees only. These are the patches which is brought from the electronics shop, electrical shop, and having only 10 rupees of that cost of this sensor, low frequency patches. And you can bring high level, high end frequency patches also. Their cost varies depending upon their capacity. So this is our one of the experimental setup which is used for the strength of that cube. After putting that sensor on that, we recorded this kind of what you say, the frequencies for before, during the temperature grading. That is frequency before damage. This is one of the case, that is before damage and after damage. After finding out, after gaining sufficient state, then we are damaged the structure and that cube, and we are gaining frequency before damage and frequency after damage. And these are the compressive strength which is depending upon the damage. If you see here, when there is a that temperature gain and strength gain is our first part, and in second part, if you see here, because we introduce the damage, then when there is a damage, is 0% damage, you can see here the compressive strength is more than when you introduce the damage is up to 400. Then if you see here, this strength damage is because of the damage, the strength of the concrete is decreasing. From that, we can predict that that sensor is very much accurately predict the strength. Then this second case, our second case is we have put this sensor on a slab specimen. Then we find out when we are put on the slab, if you see here, this is healthy state of specimen.
Sir, please share slide.
Yes, sir.
Slide दिख नहीं रहे.
It is changing, sir.
No. यहाँ पे हमको शेयर दिख नहीं रहा है.
Visible, sir?
No, yes, sir. Yes.
Okay, so this is one of our work, that is we are applied this PJT patches to the slab specimen. This is not in large scale, but it is in laboratory specimen is there. If you see here, this slab we have prepared and put, that is in surface bonded patches is there. Then we take the total and for vibration we have not what did it say, we have not that instrument to vibrate that slab, so we are in the water pump. Then this is one of the LCR meter, and we are getting the signals of the vibration, that is before damage and after damage. If you see here, the resistance is 4.6 ohm, and here the after damage it is 6.1 ohm, because when the structure is intact, then we are getting R value is less than when the structure is damaged. Then here when we applied this in the UTM machine, then we can see here also we can find out after that what are the strength changes. These are the cracks of that specimen. Okay, these are the impedance. Then we calculated what are the value you get, and after that we can find out the impedance of that. So this is what is the conclusion you get. That conclusion is like that, okay, we are getting that response, that is when the structure is damaged, then we can find out there is a less of strength. Then we find out that these PJT patches, this is our basic. When we are started this one, this is basic, and we want to know that PJT patches are working or not. From that two experiment, we are got that we received that the PJT patches are very much worked, and we also that validate this work with various classical methods, that is NNDT methods, just like that is conventional methods, that is Raven hammer and UPV test. We are just compare these two results, and we are getting that sensor is working. Then when we know that this sensor is working properly, then we go to other type of structures. Just I am going to share. Then we just see here, we are applied this methodology to one of the steel truss bridge model. In laboratory, we have tested these PJT patches, have been carried out one model, that is this is the one steel truss model. This is 1, 2 and 3 number at the location of the patches, and here we are used, if you see here, there is a vibrator is there, and we are just take one simple vibrate to vibrate that structure, because when you are going to take the signals, the structure should be vibrate, and because of that vibration we are giving use to this motor. Then after, before damage, we take the frequency, and after damage we are damaged this structure. If you see here, these black dot lines are the damage of the structure, and we just the patches is there as original. When जैसे original के time में patches जहाँ पे था, the location of the patches are same, but we introduce the damage in 3 locations, that is damage 1, damage 2 and damage 3. Why you are putting this damage? Because in sensor technology we are going to find out the damage locations also.
Mike sir,
yes sir, yes sir.
स्लाइड नहीं दिख रहा है, स्लाइड आप खाली वो स्क्रीन दिख रहा है, विंडो स्क्रीन.
सर मेरे इसमें तो दिख रहा है, आप एक बार देखेंगे.
रुको अभी ऑन किया था, शायद ऑन किया था, दिख रहा था.
एक बार आपका स्क्रीन बंद करके देखिए ना सर.
नहीं, बंद करने का कुछ मतलब नहीं, मैंने आपको को होस्ट किया है, वहां से दिख सकते हैं.
ओके,
अभी शेयर हुआ था आपको. हाँ अभी हो रहा है,
शेयर है वो.
हो रहा है.
नहीं वो क्या हो रहा है पता नहीं, ऑलरेडी शेयर है लेकिन बार बार वो चेंजेस क्यों नहीं. ओके, देन इफ यू सी हियर, देन दीज आर द 3 लोकेशंस. First 1, 2, 3, these are the PJT patches. This is before damage. This is before damage. You can see here, this is the steel model, and these 3 locations are the before damage, and we take the we put the vibration using this small vibrator, and we take the readings of that frequency and all this thing. Then we get the result. Then after that, same model, and at the same location of the patches, we put 3 patches at the same location, but we introduce the damage. If you see here, this is the damage position 1, damage position 2 and damage position 3. Why we are introduce these 3 positions? Because we are, if you remember my previous presentation, and at that time we see that not only finding out the damage, we can find out the damage location. To finding out the damage location, we are put 3 damages in that structure. So here, sir, screen change हो रहा है क्या sir? It is changing. Kate sir, my slide is changing or not?
Yes, sir. Yes, sir. Go ahead.
Okay. Thank you, sir. Then here, this bridge model again is tested. This is also these, what you say, these are the total model which is total used, that is the setup we are used. This is DSO meter, DSO, and this is the LCR meter, and this is the total model which is used for them. Then we get this is then we get the results and compare these results and finding out the location of the damage, severity of damage. Then we can find out the damage state also. Then this is lab setups. Okay, then we try to put these PJT patches and try to find out what are the response from a real structure. Then we go for one of the railway bridge crossing near this locality, and we carry out the total. If you see here, then there is a train above that train line. That is this is a railway bridge. Then we carried out these types of work, sensing technology, real-time monitoring in that batches. You just see here, this is the setup, and we take the vibrations when the train is passing under that train, and also there is a expansion joint. At that expansion joint, we provide that patches, and we just carry out the work that the PJT patches are going to monitor the structure very effectively, and we compare both the results with the experiment and with the lab result. Then this is the PJT locations. One of my students, pass out students of PG, is working on that, and these are the some numerical calculations we do. That is PJT patches and locations, and we are getting very good results. That is these are the frequency, and here in the healthy state and in damaged state, and it is the distance of the patches, that is 40 mm, 150 mm, and 300 mm. You can see here the response and all these things. Then this is the damage condition, and this is the frequency, and this is the period of vibration we are calculated after the all distances. And we have, after finding out, we have compared the patch 1, patch 2, and patch 3 for the healthy condition and damage condition, and we are getting good results. And this paper is published in a Springer journal. That is I can, if time permit, I will see. So this is my fourth what you say applications. Fourth applications using these PJT patches. Okay, then we are going to see that is we have already discussed. Then third one, that is third case study which are applied to the non-engineering structure. Third case study which is applied for a non-engineering structure. If you see here, this is a non-engineering structure. That is, what is non-engineering structure? This structure is built without any engineering concept, not concept. This is calculation.
Screen.
Okay.
Hello, sir. Screen नहीं दिख रहा है. Yes, sir. Yes. दिख रहा है.
This is my that is applicant. One more applications, that is, this is one of the non-engineering structure. This non-engineering structure is not like that. It is only the engineering techniques are used, but concepts are, the calculations are not done. We are going to check the, because why we'll take this non-engineering structure, because we need to check this application to the old structures. फॉर ओल्ड स्ट्रक्चर के लिए जो पहले था तो इसलिए ज्यादा गांव के तरफ है या रेलवे ब्रिज के पास है, तो वहां पे जो स्ट्रक्चर है उसमें लोग पहले डिजाइन नहीं लेते थे। जो मिस्त्री है, मैसन्स, the masons those who are available in the locality, they are directly constructed that work. And this structure, because of that, we are just think about that, and we are just carry out on a frame that is which is non-engineering structure. Then we are applied, just 1 minute, this is our setup. This is our setup, that is we are applied here in this location. We are applied, if you see here, these are the PJT patches location. Then we take two readings, that is before damage and after damage. So here this is the damage, after damage, this is the point of damage. Then we get the severity of damage, location of the damage, we are get from that equation. If you see here, this is that result we get after the testing, that is the frequency, that is the damage, then percentage of change in the damage, and the location of the damage we are finding out. Then same problem, after getting this one, we are just done some kind of programming in Python, and after this value is checked by the Python. In Python we are doing same input parameter जो है हमने उसमें पुट किया, और Python सब प्रोग्रामिंग हम एक प्रोग्रामिंग किए, और प्रोग्रामिंग करने के बाद हमने उसके ऊपर जो भी डैमेज के लिए रिजल्ट डाले, इनपुट फ्रीक्वेंसी जो हमको एक्सपेरिमेंट से मिला था, वी जस्ट चेक दिस experimental result after coding in Python, and we get there the result damage index both experimentally and analytically, and this will only difference is something like 0.52% is there. Then it is in that we can see that Python programming and this Python programming is going to use, and both the structure is what you say, both results are validated with two experimental result and analytical result, and we get the good answers to that result. And this paper also published in a Springer journal, that is Innovative Infrastructure Solution, and Scopus Index journal. Then whatever this is the third case, and again then this technique right now, just before some time in the previous lecture, as I told that this applications is used, just 1 minute, I am going to share with the screen. Okay, this application is used now after getting this all these results and good response, and knowing how the PJT patches is working, how the PJT patches are working. Now we are going to use these PJT patches for energy harvesting. So for energy harvesting, we have prepared that model, and we had put the AI technique also, that is energy harvesting using PJT sensor, and that technique, AI technique for a smart payment. We joined these two things, and as this is our work is going on this topic, so this is one of the payment which having PJT sensors are provided in various junction of that road, and this PJT sensor is converted that pressure into energy, and this energy is stored by here. This is our one of the model. This is that battery is provided here. When there is a passing of the vehicle, then this will be create the pressure on the PJT patches, and this PJT patches, this pressure will be going to converted into electrical energy, and this electrical energy is going to store somewhere else, this road construction, and this smart this will be used for the lighting purpose, and this energy will be saved. This is our new technique. This is one of the what we are design pattern we are published previously. This is our total concept. This working is going on right now, and this is the AI technology. This AI technology is used for the that is physically challenges persons, because the structure AI technology, the data receiving after that AI technology, this will be going to the active that physical challenge peoples can pass the roads. just मैंने आप लोगों को उस दिन एक वीडियो बताया था, and this is the development recently we are done. Okay, and this is the patent which is going to used in that time. So at that time there is a energy harvesting method. Just we see here. So there is a small video how the patches directly during our experiments. We are not recorded that how this cube and patches are applied. For that, for better understanding, I am just finding out on video. You can just see how the patches are applied to the structure. Sir, my screen is visible, sir. That is, sir.
Yes, sir.
Yes, sir.
Software for application development. By learning just 1 hour a day, you need no prior experience.
How to fix the PJT patches in the cube. In this video they are showing how to fix that, connect that PJT patches. It is the PJT patches which is surface bonded to the concrete cube. You can embed it during the casting also.
Surface bonded PJT is fixed to the wires are soldered. NCR method. This is one positive and another one is negative. This will be tested in NCR method. Sufficient line.
Then after finding out that test, then how to fix, then they are applied to the structures, and for the concrete cube specimen is tested under various load CTM, and this is technique how this one. Now I'm going to see the energy harvesting, one of the energy harvesting of Okay, at that day, we have seen that, just 1 minute. Okay, this video we have already seen 50% before our in our previous lecture. Now we are going to, after quantification of the total damage and all these things, how we will going to harvest that energy. This madam will be explained very goodly. Just see.
After quantification of the energy generated by the PZT patch, next step is to store that energy. For that, we have fabricated a full wave bridge rectifier circuit. We have connected the PZT patch here, and we are measuring the voltage across this capacitor. A yellow line represents the input voltage across the PZT patch, and blue line represents the capacitor voltage. Now, when I switch on the output, we can see the increase in the voltage across the PZT patch, and we can also observe the charging of the capacitor. When I switch off the output, the capacitor gets discharged and the input signal dies down. An 8593 circuit, which is an alternative circuit for LCI meter. For starting this circuit, it has to be first calibrated with a 200 kilo resistor. So we'll connect this resistor with the circuit and we'll give a start frequency of 50 kilohertz and a delta frequency of 200 hertz. Number of increments are okay, and we'll give internal oscillator, then start the program device registers. Okay, calculate gain factor. Okay, then measure the temperature, enable the theoretical calibration profile, and start swing. Now this blue line is the calibration curve and black is the actual reading, so they should be very calibration part is done. So we will remove this resistor and will attach the PZT patch. Measure the temperature of the PZT patch. Start the sweep. And now we can download the data in the Excel file. So real and imaginary. These are the useful part of the data. Real part represents the resistance and imaginary. We can calculate the conductance and susceptance by dividing the real and the imaginary values of the amplitude. We are planning to charge these batteries using this LTC demo circuit board designed especially for piezoelectric sensors. The input voltage required by this demo circuit board is 4.3 volts, but the voltage level generated by the PZT patch is very small. So we are working to enhance those voltage levels. When we'll achieve the threshold values, we won't be using these input batteries across this demo circuit board. So we can achieve a voltage of 3.6 volts and a current of 100 milliampere using this LTC demo circuit board.
Okay, thank you. For more details, you can go to this lab, that is Dr. as we told previously, that is Dr. Suresh Bhalla sir lab, which is already just 1 minute. This lab, you have to just go for more videos and work on the total smart dynamic laboratory. After my lecture, then Dr. Suresh Bhalla's sir's lecture is there. You can ask more questions related to that. Kate sir, over to you. If there is any question, you can add us. Kate sir? Dr.
Yes,
Kate?
sir.
Yes.
Sir is joined now, sir. Hello.
हेलो सर।
हाँ, भल्ला सर ज्वाइन हुए क्या?
नहीं मुझे भल्ला सर तो 6 बजे सर ज्वाइन होंगे। फॉर दैट इफ एनी क्वेश्चन माय सेशन देन वी कैन डू दैट।
Okay.
Bhalla sir will be join after 6 p.m.
Okay. Yes, participant can ask any question. Yes, from participants, any question? क्वेश्चन नहीं होंगे तो हम सर को कुछ ये करेंगे. So what we learn?
Yes sir.
Yes, sir. If any no questions, sir, please continue with your case study on energy harvesting. और या भी जो भी कंप्लीट सेट के ऊपर कुछ हो सकता है, जैसे कि SHM.
As I already told about the energy harvesting and more videos on this, we can go to smart lab. If you go to IIT Dr. Suresh Bhalla, Dr. Suresh Bhalla, then we can see here at that you can see there is a lab and test your EMI signature also. If you see here, then we can go and test your EMI signature. There is a ready-made link available in search site, and you can check and analyze admin signature, recent invited talks there. You can see here, and for more videos, you can go to the download some thesis also there, and smart structure dynamics laboratory is also there. You can go to this laboratory, and if you see here, these are the some model videos we are sir put in that lab, and I'm continuously watching this one. If you see here, this is the energy harvesting from the starting. This is the wind energy you see here, my screen is visible, sir.
Yes, sir. Please full screen कीजिए.
You can see here. This test is carried out on the wind energy. If you see here, this is the setup. These are the setup. This is the wind tunnel, and this is the LCR meter and digital oscilloscope. Okay, then this side is in modeling of PJT patches in ANSYS software. There is a software, as we know, there is a lot of software is available for the structural modeling and detail using ANSYS software. How this is the videos created by sir. You can see here also. This is the ANSYS modeling, and this is the input parameters which is fixed, and we can say that how this PJT patches is working. That is actually material property is very essential in that.
कौन जो हो केंदा
this is the load setup actually. What are the load setup you can see here? How to apply the load in ANSI software. This is the complete setup, which is total about how we are going to do the in ANSI software. Okay, then if you see here, okay, so if you see here in my Google Scholar, you can see that papers that is which are using this technique. If you see here, this is my one of the paper which is published using same concept, that is experimental based Python programming. Just one, if you see here, is an experimental based programming for a structural health monitoring of non-engineering structure. We can see here using same concept, that is same concept. This is one of the research paper which is published in a reputed journal, or we can do lot of work using this kind of. This is one of the paper, and what setup we are talking about. This is the total setup we have taken. That is, this is the schematic view, and this is the original structure. And when we are prepared that structure, this is the complete diagram of experimental setup, and these are the formulas, and this is the Python programming which is used for the Python programming which is used when after the experimental result. And this is the algorithm, and this is the total result and discussion of one my paper. And these are the patches, and this is the severity of damage. That is, severity of damage means there are three types of damage is there. That is incipient damage, moderate damage, and severe damage. We first carry out the less damage, then moderate damage, then severe damage. After finding out these three, then we are put the finding out the damage, what are the quantity of damage in that. And these are figures. You just see Applying these sensors technology, we can find out, we can work in various field also. This is one, and this is first one. Then if you see here, just 1 minute, I will go to that. Then another is we are not seen that this is in my PPT. This is the same technology, that is corrosion expansion sensor. We are not talking about this sensor. This is one of the project which is also published in a Springer lecture note, and this is the beam specimen which is using the corrosion expansion sensor. This is one kind of sensor we have used. This is the method of combined metal bar and putting the sensor on that bar, and this is called as corrosion expansion sensor. If you see here, then the corrosion are introduced, sensors are embedded in this structure, and this structure is sensor is embedded into that beam, and the corrosion is applied using this corrosion is applied using this setup. That is, the corrosion process is accelerated using this total setup. Then after getting the corrosion, we just read the sen using this beam specimen and oscilloscope. We are finding out the corrosion about in the beam and find out the severity also. So this is the beam specimen after and before corrosion induced by the corrosion sensor. So this is another type of work. Then if you see here, another work is this is evaluation of breeze, that already we have seen that we have published one paper in also that if you see here, this is, you see here, this is that is in Springer Nature lecture note in IIT Gandhinagar. That is, if you see here, this is the model, and this also we have published this work in a reputed journal using some these concepts. Okay. Then as Bobde sir already mentioned, we have received some of the funding also using this technique, and now recently we have that what you say, that the patent we have granted, design patent, and right now we are working on the energy harvesting, and we are applied for 20 lakhs of funding, applied for the RPS funding, and we are trying also to put the utility patent. So this is all about my work, and what, and there is another work also which is just I think I have that photographs with me. Just 1 minute. I think right. This one. This is way back before. Kate sir, can my screen is visible?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
This is what I explained this topic. This is in 2012. This is in 2012 when I get the funding from SPPU. This is the starting point of this research work. If you see here, I am applying the concept to a aluminium beam. Okay, and here we have, at that time we have no idea how to put the vibration on the structure. This is a hammer, free fall hammer, which is put on that structure, and the vibration will be captured in this thing. This is the photographs. Actually, I am very sorry that at that time we are not recorded that video. If you see in the behind of this student, there is a frame beam model. I think these photographs also with me. Just 1 minute.
या बाहेर नंबर जाऊ
Structural health monitoring using PG. Lot of work. I am just from starting. I have do a lot of work in that. Some little. This is one of the work which is not published, reputed journal, but this is the work. Okay, I think it is all okay, Kate sir. Can you, if there is some question, then we will take the questions. Otherwise, you can end the session.
Yes, participants. Yes, sir. Very well. Thank you. Participants or audience can ask this any query or questions. Yes, audience. Yes.
Okay, sir.
Wait, sir. Wait. Just a minute. In structural health monitoring, you are using PGT patches. What are their amount or what are the prices?
Can you speak loudly, sir?
You are using in structural health monitoring PGT patches.
Yes.
So what are their cost and what are the manufacturing
Actually,
units?
sir,
Where
already we have told that if you go for high-end, high sensing patches, this is high frequency patches, then the rate will be very, sir. Suppose there is what I am told you before sometime in my presentation, that if you go to the low frequency patches, it is starting from 10 rupees, and if you go to the high frequency, it may be more than sir 50,000 something else. Huh? Depending upon the frequency, what patches you are going to use, then it will be very the cost will be depend upon that patches. Then again, there is a frequency. Suppose we are going to use high-end DSO, then LCR meter, then the structure. It will be depend upon the sir, properties of that patches and all this material and equipment specification.
can feasible building or any small structures?
Sir, see, we are when I am started this work, at that time I am told 50 rupees of patches and 2 to 3,000 of building model, and all these models are constructed in our lab. That is what is in our workshop. Then it will be totally at that time 5 to 10,000. Suppose you are going to do the basics, and if you are going to do the basic of that, then it will be, I think, 5,000 is sufficient if going to in basic. Yeah?
5,000. 5,000.
Up to 5,000 you can do basic test on what you see, sir. Suppose there is a DSO and there is a LCR meter, it is available on the college. Okay. Then I think it will be maybe just patches and all these things. It will be up to 5,000. You can start the works.
Okay. Okay. Now just one last question.
Yes, sir.
This can feasible मतलब जो भी topic है SHM structural health monitoring can link with digital twins or digital models can link.
So digital twins, it is totally different, I think. Digital twins, it is the just perspective view and all these things. But sensing technology is real. Suppose in digital twins, you can see the imaginary pattern, all these things. I think it is quite difficult till that to do that actually.
Because sensors and their applications are the same in AI model or in your SHM.
We can match these two. That is digital twin using some. Suppose we are going to use that concept in digital twin. जैसे हमने रिजल्ट निकाले और रिजल्ट निकालने के बाद उसको पाइथन प्रोग्रामिंग में हमने उसको ये कर दिए, पाइथन प्रोग्रामिंग में उसका प्रोग्राम करके रिजल्ट निकाले। ऐसे जो भी रिजल्ट से ये रिजल्ट्स आप क्या कर सकते हो कि आप फाइंड आउट कर सकते हो यूजिंग दिस सेंसर्स, एंड यूजिंग दैट रिजल्ट यू कैन यूज फॉर, आई थिंक आप यूज कर सकते हो रिजल्ट और एआई में यूज करके उसका कुछ बेटर फाइंड आउट कर सकते हो।
ओके ओके ओके, मतलब डिजिटल ट्विंस का जो एडिशन है उसके साथ थोड़ा सा अलग है, इसका सेम टू सेम नहीं हो सकता है काम, क्योंकि
सेम हो सकता है, मे बी उसके रिजल्ट्स आप यूज कर सकते हो। जैसे मैं और आपको और एक हमारा जो स्टूडेंट है उसका और एक हमने जिसके ऊपर टिम्बर के ऊपर दिस सेंसर यूज किए थे, हमने टिम्बर टेक्नोलॉजी की वो मतलब टिम्बर एक करके उसके अगेन सेम फाइंड आउट किए थे कि व्हाट आर द कंसेप्ट of that structure. If you see here, I'm just going to share my screen.
In smart, okay, just see.
So we can apply this motto of that this topic is we can apply to various types of structures to finding out the total sensing technology, or you can use this technique and use this result. You can use AI techniques and all these things. It may be possible.
This is called a tensegrity structure, no?
Not intensity. Actually, it is a timber model.
Timber model.
Timber model. We have applied the PJT patches here, and again we have done the same kind of thing, that we have find out the location, severity, and all these things. And if you can find out, this is the conductance versus frequency, and this is the timber model. Again, this is one of the PG work. One of the student, this is the total location and patches where we are going to apply this one.
That means you are applied instead of that material only timber.
We are applied in concrete, in steel, and in timber, and we are also now doing the application to the energy harvesting and smart monitoring system using AI.
Okay. Okay. One last question: is there any codal provision regarding this? What do we say? Work.
There may be some foreign code, but there is no code with, suppose
Indian code
technology. There is no code.
Sensing code. I have that question because everybody have.
अभी तक मैंने तो यूज नहीं किया है, मे बी होगा उसके लिए कुछ अलग से इलेक्ट्रिकल.
If we apply this relevant code, it may be go through path channel, like what do we say, correct recommendation. मतलब सही पाथ पे वो प्रोजेक्ट जा सकता है अगर
जा सकता है. There is lot of application of this sensing technology in modern day. If you collaborate this AI technique, just like what you say that is digital, that is digital twins and AI, and you can find better results.
Okay, it's okay. If anybody video you can see that anybody that must completed structures by using PGT sensor materials, using any road, any
There is
bridge.
in Google and in YouTube there is a lot of video about the sensing technology and all these things. I am already
But
provided
that
lot of
most referred video, if available, please see anybody that is relevant to bridge only, because our point is related infrastructure.
सर बहुत सारे लेक्चर अरे अवेलेबल है, आप अगर भल्ला सर के साइड में जाएंगे
नहीं भल्ला सर का नहीं, वो उस दिन जो हम स्मार्ट मटेरियल्स का कौर मैडम का जो बात किए, अगर उसका हो सकता है।
कैन यू स्पीक लाउडली?
कौर मैडम का जो आपने बोला था ना, ड्रोन टेक्नोलॉजी यूज करके एसएचएम किया।
तो कौर मैडम अभी रिसेंटली आई हैव वन वर्कशॉप which is related to this topic, Atal FDP. Actually, this is in physical mode, and I am invited Kaur Madam, the CSR scientist, and he is explaining about the sensor technology with drone, and there what experiment they are done. They are already explaining that if you are this FDP permits, then you can invite madam and you can join and speak about that.
Okay, yes, anybody from participants? Yes, madam, please. Hello. मैम आपका आवाज ठीक से नहीं आ रहा है। हेलो।
Sir, okay. Any question is there? Can you leave?
Just a minute. Somebody is asking, but it's now not now. कोई तो क्वेश्चन पूछ रहा था, लेकिन वो चला गया।
Okay, thank you, sir.
Okay, sir. Okay, thank you, sir, guiding us regarding transforming construction and their traditional methods and their advancement in structural health monitoring of different structures, various structures. So thank you once again, and thank you all participants. So be ready with the last session from today's FDP will be started within 10 minutes, 5 to 10 minutes. Okay, thank you, sir. Your voice is not clear, sir.
Thank you, sir. Thank you for inviting and for such a nice FDP. And I have also listened to all some of the sessions which is delivered by very good experts from IITs and foreign peoples. This is very good workshop, and
Yes,
I think the learning outcome of this will be helpful to the participants.
Yes,
Thank
yes.
you and
Yes.
congratulations to all.
Yes, sir. Yes, sir. Please join, sir, last session also, but last session.
Yes, sir. Yes.
Okay, sir. Okay. Okay,
Thank
so
you.
all participants be ready with 5 to 10 minutes. Our last session will start within 5 to 10 minutes. Feedback is
येऊ का मग मी थांबा जाऊ दे तिथे.
सगळ्यांची घे बरं कसं स्टार्ट आणि Sir, may I audible? What is it?
Yes, sir. Yes, sir.
Yes, sir.
All the participants, please be ready. Our session will start within 5 minutes.
लोकल आली वडगावच्या पुढे आहे लोकल.
Good evening. Am I visible and audible?
Yes, sir. Yes, sir.
Okay. Sorry. I was coming from outside. And let me just share my screen.
Just a minute,
Wait,
sir.
sir. We introduce first of all.
Firstly.
Yes, sir. Please, Bobde, sir.
Okay. Today's third topic, energy harvesting in India, challenges and strategic roadmaps. Today's speaker, Dr. Suresh Bhalla, sir, holding fellowship in Indian National Academy of Engineering and the Indian Society of Structural Health Monitoring. Founding President, Indian Structural Health Monitoring System, founder and mentor, Smart Structure and Dynamic Lab and Structural Simulation Labs, and currently Professor Department of Civil Engineering, IIT Delhi. Sir's research area of interest: structural health monitoring, soil and structures, biomechanics and biomedical, piezoelectric energy harvesting, carbon negative construction technologies, SHM of heritage structures, AIML in SHM, novel energy dissipation devices, these underground structure adoption and transfers of aerospace technologies to civil engineering system. Sir has more than 30 years experience in industrial and academics. Sir has organized 13 plus workshop and short courses on different topics like heuristic sensing technologies, structural earthquake effects on structures, green building, 3D modeling, 3D analysis of multi-story buildings, structural health monitoring, smart materials and structures. Sir has published 3 books, then 3 book chapters, 86 international journals, 103 conferences and workshops. Sir has awarded or recognition in elected as a Fellow of the Indian National Academy of Engineering with the effect from 1st 2025 in recognition of his distinguished contribution to engineering and technology. International recognition among top 20 SHM scholars of the world. High research impact recognitions. Sir has also best oral presentation, then best paper award, then teaching excellent award also in IIT Delhi. Over to you, Balla sir.
Okay, thank you very much for your kind introduction. My slides are visible.
Just a minute. Yes, sir.
Yes, sir.
You are able to see my slides. So today I'm going to delve on a very interesting topic, that is Indian knowledge system inspired carbon negative construction technology.
Yes.
So basically here we will cover how, if we can take advantage of our ancient system or on Indian knowledge system, and we can just do it scientific study, and we can, if we can integrate the modern science and technology with our Indian knowledge system, then we gain a lot as far as sustainability is concerned. So that is the topic we have covered for today, and it tells us about our 1.5 decades of research in the area. So basically here we are using bamboo as the main structural element. So if we go for, say, beam column frame system, then we are using bamboo for that purpose. And we are using cow dung and reed. Reed is sarkanda, that we use for masonry infill. So today construction industry is one of the most polluting industries of the world. Every ton of cement, it emits more than 1 ton of carbon dioxide in the atmosphere, and same holds good for steel. So one might not think that construction industry is so much contributing to the pollution, but it is contributing to over 25%. So it's not just the emissions from the vehicles that are contributing to pollution at the industries. The construction industry is a direct contributor to pollution. Now, bamboo, on the other hand, is a carbon negative material. So if we can use 1 ton of bamboo, that means we are getting rid of 1 ton of carbon dioxide of the atmosphere, because it soaks the atmospheric carbon dioxide and it converts into very highly strong and fibrous material, bamboo. Now, if you compare the strength characteristics, now here also bamboo is quite competitive, because its strength might be less as compared to steel, but when we see strength as a ratio of the mass, as a ratio of the density, then bamboo offers a very competitive strength to mass ratio as compared to both steel and concrete. And then, unlike timber, bamboo matures in 4 to 5 years. Timber, we know if we have to grow a tree, it will take 30 years to grow full. And then when we are cutting it down, so it is gone. But bamboo is not like timber. First of all, it grows in 4 to 5 years. And then what happens is that after it has matured, bamboo is like a grass. You can cut the top portion, it regrows. It does not kill the plant totally, just like in the case of the timber. And its cultivation is suitable even in the lands which are not very productive, where other crops cannot be grown, so bamboo can be grown over there also. अच्छा कैलाश यहाँ का रहने देना. So now the issue with the bamboo is that bamboo is very slender. And we know that if the wind forces are dominant, how bamboo will bend. But it is very resilient. It is highly ductile. It does not break that easily. So this is the most important point. So it has very high fiber strength. And this fiber strength we can use very intelligently for structural engineering applications, provided if we can tackle this problem of slenderness. So we show how we have done some research. We have developed some specific combination of material in the form of a composite utilizing bamboo, and this can very easily solve our problem, and this can get us from the point of view of strength, we can get capacity as good as the conventional concrete structures using this method. Now this shows why bamboo is so strong, because it has a particular fibrous structure. If we cut a portion of bamboo, this is how it will look. And here I'm just zooming on the section. So if we point the camera here, microscope here, so this would be the view we would observe in the microscope. And if you further zoom here, the red ellipse, then this is the further microscopic picture. And if you cut a section from here, we'll see these fibers. So these fibers, they are very strong. Their strength, the individual fiber strength could be as high as minimum 500 megapascal. So another problem with the bamboo is the jointing. How do we make the connections? So if we can solve the problem of connections, and if we can solve the problem of the slenderness, then we can achieve a lot with bamboo. Of course, bamboo is a biodegradable material, so it has a fixed life. If we can do a little treatment, and if we can do some protection, then bamboo can last for at least 30 to 40 years. So this is a summary of the problems we have just seen, and we see how we can address these technological gaps, how we can eliminate the deficiency of the single shoot bamboo, which is very slender, and then how do we develop sections making use of bamboo such that the capacity, flexural capacity, the tensile capacity, compression capacity, this is comparable to say reinforced concrete and steel. And then how do we integrate the rigorous principle of structural engineering so that we can have a very quantitative assessment of the capacity with reliability? Because if we have to bring this in the design industry, then we must tell that, okay, if this is the bending moment, then this section you would require in a very predictive manner. Then only the structural engineering community will accept it. So we have addressed all these problems in our research, which is more than 15 years old. 15 years ago, we started on the bamboo, and now we have reached such a level that we have now a startup. So what solutions we have proposed is, we have proposed some solutions for shed type structures, which are light in character, which have light weights, light loads. So for that, we have these battened connections. Then we have high capacity uh, type of members also, which is fiber reinforced bamboo composite. And for very small structurally uncritical structures, we can also have some common solutions. So for shell type structures, this was our original design approach, that we thought that we'll use the working stress method. We'll use a factor of safety of 4, and we consider linearly elastic behavior, and the allowable stresses with this factor of safety, they'll be 1/4 of the characteristic strength, and that should be based on actual measurement. Now we have a bamboo code also, and this code even specifies that if you are dealing with certain species of bamboo, we can adopt certain strength. So strength characterization was the first topic we addressed when we began this research, and we chose few species, and we were doing very large number of strength tests, and we did here. And also our collaborator from Trinity College, University of Dublin, he also took some specimens and conducted some tests over there. So we got not a very unique type of behavior. There was variation, and if you want to statistically and scientifically take into account the variation, then we have to do proper statistical analysis. And some of the tests which were performed in Ireland, so we tested 2 species. One species was giving an average characteristic strength of about 76 megapascal and other 61 megapascal. And then we carried out the characteristic strength determination. So we got some values for the 2 species, the Dendrocalamus strictus and Bamboo pallida. And the tensile strength test was a problematic one. So we tried to use the same machine which we use for steel. So for that purpose, we cut the bamboo vertically into these smaller sections like this. So here the entire cross section is divided into 3 verticals, and one of the verticals is fitted at a time in the UTM and tested in tension. So we carried out this test, and we found some kind of behavior, and the strength, we got the strength value, but what we noticed was that this was an underestimation of the strength, because here the failure was not necessarily a tensile failure, but it was the crushing of the bamboo. So we were satisfied that whatever strength value we are getting, it is on the conservative side only. So here end splitting, for example, that was the dominant failure, and so actual tensile strength would be much higher. So these are the results of the tensile strength. So we got characteristic strength around 76 megapascal for Dendrocalamus strictus and 62 megapascals for Bamboo pallida. And then once we have these values, then we use the simple working stress steel design calculations. So this was the first structural system we thought that we'll make a triangle, top triangle like this, and this will fit into the column. So we thought that best is that in the beginning we have hinge connections like this. Rather than going for a truss, we just go for this kind of system. Just the external members are there, no inside members like the Pratt truss or other. And we did full wind load calculations, wind analysis, and we calculated, our students, they calculated the bending moments, the expected tensile forces, and the shears. And based on the strength we got in the lab, so we configured that this cross-section made up of 6 bamboos. So basically, if there is a bending moment, we convert that into push-pull, and the axial force we divide into the 6 columns. So that simplified analysis strategy, just like we used for steel, we used. And then our students, they made prototype columns like this. So these are the batten columns. So here, basically the battens are made up of bamboos, and they are joined by this kind of simple connection. So we'll see in detail. So this is the batten column ready just outside my office, and this is how the connections are done. So we have these bolts, they are passing through these half split bamboos which are acting as battens. And this is the same column under test at Trinity College, University of Dublin. And then the top chord and bottom chord members, they were also designed. And this is the test result from Trinity College, Dublin. So we found that these columns, they are good in axial compression. So we could get load capacity of around 20 kilonewtons. And then we had instrumented with strain gauges. So we got good result. And this is how the battens are fixed. So in one case, we have only one hole each end, other case, we have two holes. So the test of these was also done. And the two-hole system proved to be much better as expected. And now how do we connect it with the base? So we thought that let's make this system a very flexible one, so that at site we can go and erect it. Let's say we fabricate everything in the workshop, then we take it to the site and erect. So the only possible way was that we integrate something with steel. So we thought that let's say we have steel base plate, just like in the case of the steel structures, and on these we fix the bamboos. So I'll show how we have done it. So this is our foundation system, and here we are leaving the anchor bolts, and then we have this kind of beam, this kind of bamboo steel connections. So what we see here, these students, they are tightening these bolts, and then this is a kind of a clamp which is just getting adhered to bamboo and getting fixed. So there is no use of any adhesive, so it's just the friction base. And we have used these threaded systems so that there is a higher amount of friction nor interlocking. And then there is no drilling, because this involves such a system that there is no need of any compulsive drilling in the bamboo. Because if we do a drilling in the bamboo, then that reduces the strength. So it's a pure friction based connection. And now it's very important that we check the capacity of this kind of connection. So that's what we have done. So we tightened the nuts and bolts with a very fixed top, so that we quantitatively determine what way we tighten them. And other thing was that we remove the top fiber, top sliver, because top sliver is very shiny, and its finish is very smooth. So if we remove that, then we get a higher, because then the threads in the cups, they basically fix their teeth on the bamboo. So we remove the top fiber like this, something like this. So this makes it a very friction based connection. And we tested these joints. So we found that we could get good strength. Typically, we are getting up to 35 kilonewton of the strength with this system. And what we found that the final capacity depends on what torque we apply. So our suggestion is that any torque between 15 to 20 kilonewton meter is sufficient, because we get a good amount of the peak load. So what we recommended that we should have a bamboo with outer layer removed, outer skinny layer, the shiny layer of bamboo should be removed. Then we should use thread clamps, and the best torque is between 15 to 20 Newton meter. We applied beyond 20 Newton meter also, but we found that this causes the bamboo to little bit crush. Now this has to be determined based on what species of bamboo we are using and what is the diameter of the bamboo and the wall thickness. So it has to be determined from the actual site testing. And then we made the fabrication of this frame, very simple frame, that we have the columns which are fixed at the base, and then at the top we have this triangular simple 3-element truss system. And then our students, they did construction. So these are the reinforcement of the foundations, and here the foundations were cast. We did not bury them inside, so our objective was that they should be visible to the people from outside. And then we have our framing system with these bamboo columns fixed inside this steel shoe at the end. So this imparts a limited weldability. And then we fix these here. So now imagine we have everything prepared in the workshop and transferred to the site and fixed. So we have very strong and very rigid connection like this with the base plate you can see at the bottom, and the bamboo is fixed here. So these connections, there are 6 combs, and each has a capacity of 40 kilonewton. So we can now see how much moment this can carry. And then we have the upper portion. So upper portion is fixed on the top, and then this is the splicing. This is splicing. Of course, you can see some rust also, so that was removed, and there was a primer, red oxide primer done. And this is how the thing was pulled at the top. So what we found, that this system was too heavy, because the addition of this bottom member, it was creating some issues. So it was making it too heavy, and we have to have a splice also. So then what we did was that we thought that let's have a lightweight system, and that is possible if instead of the hinge here we can have a fixed rigid joint, just like a portal frame. So on this we worked, and this was quite successful, and this is the frame ready. So this frame is part of the light battened bamboo system, LBBS, and this technique can be used for multiple constructions which are lightweight, just like shed type structures. This is very good. So it has the flexibility of pre-engineered construction. Then simple friction joints are there, lightweight, simple erection at side, and the wind effect is also less severe as compared to the earlier arch kind of roof. Earlier, our collaborator, he used to have these kind of arch kind of roof with these concrete battens, so that used to make it very heavy. It was developed by Dr. Sudhakar. But then our is much sleeker. So this was part of our project, a World Bank funded project, which operated in 2008, 2013. So all this work was done as part of that. So it had specific objectives on the study of the rheological properties, on shaping bamboo, on investigation of existing bamboo structures, and development of cost-effective equipment, and design, development, and demonstration of bamboo-based selected applications. So objective number 5 we were doing. We were interested with objective number 5. And we had a number of collaborators in this project. IIT Delhi was there, Central Power Research Institute, INBAR. So they were part of this consortium. So after this project was finished, we continued our bamboo research. We had PhD already started, and our next goal was that can we use now bamboo to make multi-story buildings, because that was the challenge given to us. That fine, we can make simple those structures which are light battened bamboo system, but how about multi-story buildings? Can we construct multi-story buildings also with bamboo? So we addressed this challenge by this invention, which is fiber reinforced bamboo composite, and this has been scrutinized by a thorough peer review of the technology internationally, and we filed a patent in 2022. So basically, what you see is that here it's a system. It's actually a system of the bamboos which are joined together in a composite action. And our objective was to get capacity in flexure, tension, and compression almost of same order as concrete. So this is the fabrication process, and this is a beam fabricated. And our first objective was that we have to get a composite action. So composite action means that this entire system should behave as a single unit. Each of the bamboos, they should not behave as individual bamboo columns, but they should show composite action. So bamboo at the top should be under compression, and the bamboo at the bottom should be under tension completely. So we had to go through several trials and errors, and in the end, we could achieve this composite action. So this is the test. The test result we are showing here, that we get a perfect composite action, and this is on account of the perfect bonding and the joining of these matrix. So this is like a matrix of bamboos. And the next step was to develop a design approach, that some kind of calculation by which we could calculate how much is the moment capacity. Just like for RC structures, we do calculation of the ultimate moment capacity, and for columns we also do the calculation. So similar calculation we propose, and this was validated with experimental results. Once we worked on the beam, now next part of the problem was to have a connection, because connection holds the key. So for that purpose, we conceived this way, that we have these individual beams and individual frame members, and we use a little bit of steel and some epoxy, and we make a connection system like this. So the point was, what should be the filler material in this joint? So we wanted to avoid concrete, because concrete takes 28 days to cure. So we propose that we'll add here steel like this, bent steel, which is going inside the bamboos, both beam and column, and this space we'll be fixing with epoxycrete. So epoxycrete is something that we use the epoxy, we use the coarse aggregate, we mix the two, and this becomes epoxycrete. And it cures in just 24 hours, 24 to 48 hours. So this is another kind of beam where there are basically junction has 3 members. Now this is how the system appears. So all these are polypropylene fibers, and after the epoxycrete is done, then this is how the structure appears. The joint appears. So this joint was tested, because the effective test is that joint should remain rigid. That is the relative angle between the two joining members, that should not change from 90 degrees. So this is what we achieved. And then we made these 3 full-scale frames, because our next objective was to test them at Trinity College, University of Dublin, because they had a full-scale testing facility. So we instrumented them, and then the frames were transported to the structures laboratory, Trinity College, University of Dublin. So the frames, they were tested under lateral and vertical static loads, along with the strain and deflection measurements, and all joints were rigid. So this is our instrumentation scheme, and the frames, they were unpackaged at the Trinity College, University of Dublin. This is the test setup, and they are being fixed at the proper location. And now we are reading the frames for testing. And what we did analysis using the plastic analysis method. And we because we knew the MP, or the plastic moment capacity of these systems, so we could calculate, we could estimate what would be the failure load in the horizontal and the vertical directions, whether it's the beam mechanism or the column mechanism, or the sway mechanism, or the combined mechanism. And later on, when we carried out the test, we could find a good estimation. So this is the frame under combined mechanism. We are applying a horizontal load and also vertical load. And you can see here the plastic hinge formation. Combined mechanism is there. So this is the frame with the combined mechanism. It felt like this. So it had a combination of the vertical and the horizontal loads. And then the next frame was in the sway mechanism, the pure sway. So you can see here no vertical load. And here, this is where this beam landed, this point. And the third was again combined mechanism, and it landed here. So it had less of horizontal load, more of the vertical load. So basically, what we could observe from these tests was that we could get different mechanisms, depending on the combination of the vertical force and the horizontal force, and we could get very exceptional performance and behavior and loads. So the failure was never a brittle, and it was very ductile. So the bamboo members, they were able to estimate huge amounts of force and deformation combined, and they could tolerate, they could absorb huge amount of the strain energy, and they could go much beyond the peak load stage. So the important point was that we could see a very high degree of ductility and resilience. Now this is very important because if our structures are subjected to wind and earthquake, then they are expected to show high ductility so that they don't collapse prematurely. And another point of observation was that even if they undergo very large deformations, once the loads are removed, they slowly recover back to their original position, original shape, without any major rupture. And this is not even seen in any RCR steel structures. So then we worked on the non-critical components. So these non-critical components mean those kind of structures where we don't need to perform a very rigorous analysis, because here there is no such problem as loss of life and property. So less critical structures, like these are small size structures with lightweight and negligible external loads, which are temporary in nature, and we can skip detailed analysis and we can have a ready to deploy design. So our students, our BTech students and some school students, they came to me and they thought that can we make a geodesic dome kind of structures. So this was very much possible, and the students, they just use our bamboo, and they basically made these pentagons. By joining these pentagons, they could make the dome, and basically they invented this kind of simple connection. So we have here an eye bolt at the end, and these eye bolts, they could be combined very easily by these basic hardware materials available in the market. And this is how a joint would look like. So we have these end eye bolt, and these eye bolts, we can again fix a nut and bolt inside, and we get this kind of connection. So this was very much feasible, and this was all done by school students. All done by school students. And they came up with this kind of dome. And in the second attempt, they got much better. Yeah, this is the second attempt. They got it much better, and they covered it with this jute fiber. And this is another example where they are used polymer covering on the same. So these have applications like in temporary sheds, temporary shelters, or animal or cattle sheds, greenhouses, solar houses, etc. Small uses. So here we are not doing very rigorous analysis. So the students, they took up this design to Shanghai Expo, and they made a small sample of this, and they won third prize over there. And this has other applications. For example, one of my students, he is working with the idea of the tunnel dome. So it is not spherical, it is elongated in horizontal direction. So it makes ideal for some of the kind of structures. So this is another example. And then this is another example of tensegrity structures. So tensegrity means that we have we are using these bamboos as compression members, and then they are basically floating sort of in the tension members, which are thin cables. So this is also very much possible. So I'm just going through this. So this is the complete bamboo tensegrity structure. And then one of my BTech students, he thought that why can't we make a cycle out of it? So he made the basic frame with bamboo, and then he used the other components of the cycle as it is. And he did testing also, both static and dynamic. And then this can also be combined with these kind of propellers so that it can, propel also using solar battery. So here we have all the students together with Professor Roger West, our collaborator from Trinity College, University of Dublin, where we have an MOU with them. Now after this, then we had next project in 2018. So this was development of engineered bamboo structures technology for modular rural housing towards sustainable built environment. And this was under the imprint scheme. So the project had two directions: one high capacity requirement and lightly loaded structures. So we had the FRBC, but we thought that let's now convert it into something very tangible and a demonstration house. So its main objective was that we should now raise the technological readiness level to 9. And this is possible if we do a full prototype demonstration. And if we can propose such a house, which should be FRBC base, which should be wind resistant, earthquake resistant, and it should be affordable for a typical rural family. If the rural family has agricultural land, they have few cows from where they can get cow dung. And if they have a bamboo plantation, then with some manpower, typically 30 to 40 man days, they should be able to erect a small unit house by this technology. So we went on this, and we thought that let's do it. So we did complete 3D modeling and all the load estimation, including finite element analysis. And we already had the experimental results, and we modeled it. And then the main thing was that we wanted to make a prototype structure. So we thought of hexagonal system, and there is a reason why I go for hexagonal system. I'll tell you later. So for this, complete analysis was done, and our objective was that if we can have a hexagonal unit, then we can expand them laterally and vertically. So for the fabrication of the prototype, what we did was that we demonstrated that all these FRBC elements, basic elements, they can be fabricated in the factory, and then they can be transported to the site like this. And then we have the foundation, and on the foundation we have the plinth beam, and then at the top of the place of the foundation, these members, they can be erected. So what we have done is we have inserted reinforcement, and the reinforcements are tied with the bamboos using epoxy, and then these are fixed like this. And then we bring here heavy machinery crane, and using crane we do the erection process. And then we have the joint. So at the joint we do in situ jointing by epoxycrete, because of epoxycrete can cure in 48 hours. So in 48 hours we should have the basic frame ready. So this is the basic frame ready, and here is Dr. Diwakar Bhagat, who completed the PhD and who was my collaborator in this project. So it is his technology, and now this basic frame is ready. So this is a not an ordinary frame, but it's an engineered frame. We know its capacity for earthquake resistance, for wind resistant in a very quantifiable manner. And I'll just take you through the slides. And now this is how what we have done is we have done the sealing so that the moisture should not be trapped inside bamboo. So as long as we can keep the moisture away, then bamboo has a long life. And we have left these reinforcement so that in the event that if we want to expand them vertically, same structure can be repeated on top of this. So that is the purpose of leaving these reinforcements. So this heals, it cures in 48 hours. And now for these members where we had kept the reinforcement, we have these kind of system. Now, these are not FRBC, but these are like, these are not, at the same time, they are not LBBS. So they have these kind of finite locations. They have these solid system. So we call it as a hybrid. These are the hybrid members. They are not the light batten bamboo systems. They are not the FRBC system, but some kind of hybrid. So then at the top, we created the roof. I'll show you the roof. So the key advantages are, this is environment friendly, speedy construction, factory production, so high quality. So it's frame structure, so much better performance and quantifiable performance under earthquake wind. Now the walls is the next thing. So we have the very fast curing of epoxycrete. So let's go to the wall, what we thought of the walls. So for walls, we had number of ideas that why not we use geopolymer masonry. But at the end, what we liked the idea was cow dung based bricks or Gocrete bricks. So this is Dr. Shiv Darshan Malik. He is the inventor of this Gocrete brick technology. So we thought that why not we use his bricks and see if they are gel with us or not. So what we find that these are the cow dung bricks. So these cow dung bricks, they are made of 50% cow dung. So cow dung is also something which is associated with methane production. So if cow dung is burned, it produces methane gas, and if it remains, then also it slowly emits these greenhouse gases. So if we can make use of cow dung in producing bricks, then what we are doing is we are preventing all this exhaustion of the gases into the atmosphere. So these cow dung bricks we have joined here. So 50% is cow dung, then 40% is clay, and 10% is lime. So these gel very well with our framing system. So what we have done is we have used two kinds of joining mechanism. You see the front wall is joined with cement, and the side wall, adjacent wall, is joined with cow dung itself. And this is our final structure which is constructed. Of course, in between we discovered some problems also. We found that the cow dung bricks, they join very well with cement mortar. But if we are instead using the cow dung mortar, then they are showing some problems. So why we go for cow dung bricks? They have better thermal insulation, they are lightweight, they don't need any baking. So energy saving and green. Otherwise, in the red bricks, we have to put them to fire clean, and that itself is energy sucking process. It emits gases also. So here in the case of the cow dung bricks, we don't need any kind of heating. So it has a negative carbon footprint, and it can be a very good source of income for dairy farmers. They can use the cow dung. So our next goal is that why not go for 2-story and multi-story, and why not make small bridge also. So we have some designs ready, and then all these why we have chosen hexagonal structure, because honeycomb structure hexagonal. So we can always go for expansion, lateral and vertical. So if the farmer is there, they have some money, they make one unit and they get more money, they can expand horizontally and vertically in both directions. So idea was that eventually we'll have this kind of system. So the other thing was the light batten bamboo composite system. So this we had been testing, and what we found that these can also be joined in certain combinations, so that we can get some good applications. So the epoxycrete, what we use, it cures in say less than 48 hours. So that's really a good thing. And we have tried something for the roof also. So roof, we can use this kind of system with these bamboos, uh, packing one on the top of other so that they are watertight. And on the top of this, we can have a coating of again cow dung, clay, and lime. And then we can paint terracotta on the top. So then we have also done on the hybrid system. So let me just show you how you combined LBBS to make hybrid system. So hybrid system, which I had shown earlier for the roof. So we don't have the fiber reinforced bamboo composite all along the member, but it has been done only in selected pockets. Say like here you see in 3 places it has been done. So we tested this. So this was not found okay. So we made it 4, and with 4 we got very good behavior, composite behavior. And then this is the 2 kinds of walls. One is the wall, cow dung brick wall joined by cow dung mortar, and this is the cow dung brick wall joined with cement mortar. So what we found that we get a better strength for the cow dung bricks joined by cement mortar. Now, if the cow dung bricks joined by using the cow dung mortar, we encountered these kind of problems. Now, some twisting happened, so eventually we had to break this wall, and then we use Sarkanda. Sarkanda is this reed, so we made these reed walls, and now our structure has been ready fully. And on the top, we have very thin 0.3 mm GI sheet, and on the top of this, we have erected again 100 mm thick cow dung, clay, and lime uh, coating. So we have got international recognition. FRBC, our paper has been internationally recognized and linked with the United Nations Sustainable Development Goals 9, 12, 13, and 15. And we have published several papers. So basically in research line, we all hinge on peer review. If our technology is fit or not, we submit in a journal, and then it goes to reviewers, which we don't know to whom it's going, and they do very strong peer review of our technology, and then it's published. So that means that yes, our technology has undergone a critical peer assessment. At least that satisfaction is there. So here we had an international student, Kayanta, and she is an architect. She made this kind of one studio apartment kind of design. And on the back side, we have Colonel Anuj Singh, who worked on this project. And basically, he achieved the hybrid system perfectly well. And these are some of our publications. You can always have a look. And the full list is in my website. So I think I just stop here and we can have some question answers. So let me again take you back to our completed structure, because we are doing some more touch up, and next week we plan that we'll get it inaugurated by some army personnel. Yes, so this is our completed structure. So the walls, they have been plastered. So plastering is again done using same mix, cow dung, clay, and lime. And what you see here on the color is the natural color. It is whitish because of the presence of high lime content. And you see the reddish color. Reddish color is essentially surki. So surki is applied on the bamboos. And then we have the LBBS system also, just for demonstration. It's erected on the side of this. And then the pathway is also made with same bamboo, using the cow dung, clay, and lime. So I think I just stop here and we can have questions. So I see we have a total of 90 plus participants.
Yes, sir.
So
Yes, sir.
any of the participants has some questions? Please
Sir,
feel.
Bhalla sir,
Yes.
it was nice informative session, and we are waiting from till 2 days, last 2 days. It was
Okay.
very wonderful session, and we think about this is maybe 1 hour, 2 hour, maybe 3 hour session, but it was very good, sir.
Oh, thanks a lot.
Yes, sir. Yes, sir. So participants can ask any query or questions, please.
Hello.
Yes, please
Sir.
introduce yourself.
Sir, actually,
And come on the
Nayak
camera.
here, sir. Hello.
Hi. Hello, Mr. Nayak.
Hello, sir. Thank you for inviting us, sir. Thank you for accepting our invitation.
Oh, it's your pleasure.
Actually, before you, sir, I am delivering 2 lecture about sensor technology, following your all concepts. That is, what is what are the sensors and what are the application we made on that thing. And deliberately, I told Kate sir to schedule my schedule before you.
Yes, yes. But due to
that was
technical
very good.
problem, that program was shifted.
That's why I chose this topic, because I did not use piezoelectric materials topic.
Yeah,
because I know that Kante sir and
yes. Kante sir actually not in the director person in this workshop. We have Mastagar sir is one of the speaker. Today he is take one of the session. And because of this online session, there is some experts from outside of India. And some from the industry actually. Thank you, sir. I know. Okay, sir, take.
Yes, sir. Yes. Yes.
So, if you ask any question, just please come on the camera, and you please feel free to ask. Just introduce yourself.
Yes.
And if you are visiting IIT Delhi, then you can visit our model structure also. Next week, we are going to inaugurate it.
Yes, sir. Yes, any participant can ask questions, because very informative and energy harvesting. Yes, sir.
Hello, sir. Good evening.
Hello, Dr. Vagish.
Yes, sir. Yes, sir. Good evening, sir.
Good evening.
Sir, actually, you were talking about bamboo structures and all, no? The bamboo structures and all you were talking, no, sir?
Yes.
Actually, I was in the Northeast earlier. The problem was of fungus. See, because of fungus now, bamboos now they used to get what I can say, this one, how to protect them, like.
Basically, bamboo, there are 3 things which we have to protect. One is the borer and termite.
Yeah.
And the third, fungus, you said, fungus comes if they remain wet.
See, in the
they
region
remain wet,
Northeast,
then
there is
fungus
this one, no, sir. Always fog and all. Therefore, that we can't avoid.
Yeah, so Delhi, we have used, for example, in our case, you saw our bamboo, the LBBS system. We say it is the same system we made in 2010. So it has survived for 15 years. So what we have done is, there was no termite treatment. We did not do any termite treatment. What we did, we applied surki, reddish color. You must have seen everything was red. So that is surki. And we found that this is environment friendly, and this attains a good protection. So it's very important that bamboo should be exposed to air. So if there is a rain, bamboo will get wet, but then it should get dry also. So if we have, we keep this letting that, okay, even if bamboo is wet, after some time it will get dry, then it can survive for very long periods. And then we should also do regular cleaning. Regular cleaning. The point is that if we do termite treatment is very expensive. It's not just expensive, but another issue is that it's highly toxic in nature. I remember that once we wanted to do termite treatment within our campus, and we were not given the permission from the environmental working group because it's so toxic. So the point is that neem oil is one suggested product which is advised that we could apply on the bamboos before fabrication.
Yeah.
And then this we already have this like FRBC. We are using some epoxy. Epoxy itself is again a toxic. So now what we are doing is we are trying to replace epoxy by PLA, polylactic acid. And we have got very good success. That I have not presented, but we have initial results where we have replaced epoxy by polylactic acid, and we have got very good results. So thing is that slowly we are moving forward. And then we have this demonstration structure. So we have deliberately, once we fabricated it in 2000, during COVID, we fabricated 21. And after that, we started fabricating the walls. But then we deliberately left it. We did not do the touch-up because we wanted to see how they behave in the real situation. When there is rain, very hot temperatures in the summer, then we have the wetting rains.
Extreme weather
then
conditions.
We have extreme winter. So we subjected them to multiple cycles. We found some deficiencies and we took steps to control that. For example, we have the cow dung walls. So some walls we use the cow dung itself as the mortar. Some cases we use the cement. And then we found that if we are using cow dung as the mortar, there are some issues. So we corrected that. So this is an ongoing process. And thing is that as we build, as we use, it will provide us more and more practical experience and validations.
Sir, one more thing, sir, actually.
Yes.
See, the lifespan of this one is just 15, 20 years, even after treatment. Whereas our conventional concrete structures is 100 years.
No, it's not 20 years. See, this is a frame kind of system. So if we are making FRBC, it will be at least 30 to 40 years, the FRBC. And the bricks, cow dung bricks, they don't have so small lifespan because there is nothing to the reinforced concrete. The problem is because of the reinforcement. Reinforcement undergoes corrosion. But here there is no reinforcement in these bricks. So these bricks, first of all, they don't have embodied energy. We have not used fire kilns to heat them. So they are just dried in the sun. So I don't think the bricks themselves, they have so short life. Now the frame system is needed only if we have 2-story or more. If we have single story, there is no need of the frame also. For single story, we can just use the cow dung bricks, and on the top of this, we can make a roof. So that will very easily last for 40, 50 years. And now see the costing. Costing, if we see that even if it serves for 10 years, we get the life cycle cost. Because our objective is that if we have a small farmer who has a small land, so he does not need clay from outside. Clay he gets from inside. If he have 5, 6 or 10 cows, he gets the cow dung inside. If he has his own bamboo, all he needs is just 20 to 30 man days of the manpower. So that is what we have target for the technology, that these people who are the real farmers, they would use this technology. You are mute. You are mute, Dr. Vagish.
Sir, the last one is, see, the vertical growth is the need of the hour now. Because of the population.
Yeah.
What is the maximum story we can build with this?
The structure which you see, we have designed it for the 2-story full seismic analysis and wind analysis. So theoretically, there is no issue. Only thing is the practical, how much we can go. So we can do the calculations. Only thing is that sections will get thicker. So I don't think there is any problem till 3-story. There is no problem.
Is there any IS code, sir?
IS, this one bamboo code is there for bamboo, IS 1581 something. So that code is there for bamboo. It's there.
Thank you, sir.
We can use that.
Thank you.
Welcome. So any other question? And please provide us feedback, because this is the peer review. Like Dr. Wagish, he raised very important points, and these give us very good points that these are the questions the end users may ask. And sometimes the users ask about the fire resistance. Fire resistance is another thing. So the thing is that these cow dung bricks, once we are mixing with clay and lime, so they undergo chemical reaction. So it's no longer now a cow dung. So these bricks, if they will not burn like the cow dung burns. People think that they will burn like cow dung. No, now it's a different thing. Now they undergo pozzolanic reaction, and a third thing is formed, and this is fire resistant. And if we have the FRBC elements, those FRBC elements, they are in the at the edges. They are just the frames. So they are bamboo is not covering the entire wall. It's limited to only the locations where there are frames. So any other question or any other idea if you want to give with these structures? We are here, our team is there, and they can do experimentation. So by discussion only all these ideas come, because we were experts with the bamboo only, and then the cow dung idea came by these kind of discussions. So cow dung and bamboo, they form very deadly combination, because both these things, they are natural biomaterials, and they are now helping us to conserve nature and make completely green structure. Okay, I just forgot to inform that we have a startup now in this technology, IKS Technologies Private Limited. So that startup is formed by me and my student, and we are now taking up real life consultancy projects regarding these kind of green structures.
Yes.
Good evening, sir. Dr. Narule speaking.
Good evening, Dr. Narule. Yes, you are from where?
VPKBIT Baramati.
Okay, Baramati itself.
Yeah. Sir, in FRBC column, each bamboo is to be covered by FRP?
No, basically, we arrange the bamboos in a matrix form. And then there are gaps. When there are these round bamboos are there, then there are gaps. So in those gaps, we basically fill polypropylene fibers and some joining agent. So in the present situation, we have used epoxy, but now we have found a very good replacement epoxy in the form of PLA, polylactic acid.
But suppose we want to strengthen the bamboo by FRP, then
sorry, we want to what we do with bamboo?
Strengthen.
Strengthen the bamboo with
FRP. In that case, can we use it FRP strips?
I mean, you want to apply FRP all around, wrap all around the bamboos.
Yeah.
I would not suggest it, because what it will do, it will basically steal the breathing ability of the bamboo. So bamboo gets trapped inside.
Okay.
So once bamboo is trapped inside, then it reduces the lifespan of bamboo.
Okay.
Like in the 80s, the experiments were tried that use bamboo as a reinforcement.
Yes.
So what happens is that once we are putting bamboo inside concrete, so bamboo gets locked. Bamboo gets locked. So now it does not have breathing ability.
Okay.
If there is, otherwise bamboo is open. Even if there is a rain, then after some time it will dry and bamboo will recover. But once it's trapped inside, then it very quickly rots.
Okay.
So this is the thing that we have found from we have learned. So that's why we propose a technology where bamboo is exposed. Bamboo is not hidden anywhere, but it does make a case of let's say if we have we wrap around. Wrap around is also a good idea. That it will definitely increase the strength. At least the instantaneous strength will be increased, but then we have to see the long-term performance. Long-term, what happens if there is any anything trapped inside, any moisture trapped inside, then that will cause havoc to bamboo.
Right. And again, it is difficult at the time at the junction of the joints.
Yes, at the junction also it will be difficult because the junctions, they are not regular.
Right.
And junctions, they are epoxycrete, very, very strong. So junctions, there is no problem.
Okay, sir. Thank you.
Oh, thank you very much for your suggestions. Any other suggestion? Like Dr. Narule, he gave a very good idea of the FRBC with FRP. So any other suggestion? Because our lab works on suggestions. We get suggestions and we can always do experimentation here.
Yeah. Yes. Yes. Any other? Yes. Any other participants? Yeah. Balla sir?
Yes.
Thank you very much.
It's
I
our
have
pleasure.
one question, sir.
Uh-huh.
In sustainable engineering works, we can do a lot of work like using bamboo material or maybe some natural material. But is there feasibility to how many days it can retain, or what is stability?
The lifespan you are saying?
Life stability.
Lifespan, I think very easily, I am saying on the conservative side, 30 to 40 years is very easy.
Okay. Because
Usually,
slab
here
concrete.
there is no issue because even if we demolish it,
okay,
even if we demolish, we don't have to find any waste site, any dumping site, because it's all it will cling with the natural surroundings. There is no point of any contamination, pollution.
Yes.
Especially with cow dung. So cow dung bricks, they grow with time because lime, it becomes stronger and stronger. See, concrete gains strength very fast, 28 days. This
recyclable.
Basically, yes, it's recyclable. So this gains strength very slowly, and eventually in 1-2 years time, it becomes stronger and stronger. The bamboo and the cow dung thing.
Yeah. Okay. And one more also that you explaining about the natural material and their testing and more test results are seen here. As well as some applications are given. It's very appreciative work, sir. Because in some private colleges, these platforms are sometimes may not available. There are some availables, but there are some lot of issues. in your laboratory work are very nice and thoughtful. So I thank you to for accepting our invitation and
Oh, it's our pleasure.
delivering such session.
Thank you.
So
I think you have very big audience, 94. All these participants, they are from Baramati area?
no, sir. It is overall India.
Oh, really? Oh, okay.
Overall
So
India.
you have, I think,
Actually,
very good participation, 95 plus.
95
And
plus, no, that is total participant 160 plus.
160, okay.
So there is,
And how many days? It was for how
this
many
is
days?
last 6 days. That is
6 days,
starting
every day in the
5th
evening or whole
January.
day?
This is 5th January to this 10th January. 6
So
days.
every day from 9 to 7, 9 a.m. to
No,
7.
6 to 9. Every day 6 to 9.
Okay, every day evening.
And last day there is a starting session from 2 p.m. to this particular 8 p.m.
Okay, so every day evening time so that people can come from the office and
Yes,
they
yes,
can attend it.
yes.
That's very good.
Yes.
That's very good. So it was done in the online manner, not offline.
Yes, no, totally online. Totally online. This
Okay,
is
okay.
online. Atal FDP is AICT sponsored. Only online.
Okay, only online.
Yes,
Okay.
yes, sir.
But now you can also try for the offline because in
Yes, sir.
offline you
Yes,
can
sir.
get
Yes,
hands-on
sir.
experience,
Yes, sir.
some
Nayak sir and
experimentation and other.
yes. Nayak sir and we discussed in future we in collaborative your session may be organized in our college or maybe Nayak sir college regarding this structure.
Yeah.
Yeah, and it will try to within upcoming year or maybe 2 years.
All right.
Yes.
That will be good.
Yes.
I keep visiting Kamal Nayan Bajaj.
Yes. VP is Kamal Nayan Bajaj, but our college is apart from Kamal Nayan Bajaj from 15 kilometer.
Oh, really? It's because I am very in close connection with Dr. Chitranjan Nayak.
Yeah.
And his former supervisor, Professor Khante.
Yes. Khante.
So, and Professor Khante's supervisor was Professor Rode. And that is in Indore. So, we have very good connection with them also.
Yeah. Yes. Yes.
Yeah. Any other question? Someone is asking any question?
No, sir. I think there is over. Yes. Any participants? Any questions? Okay. No issue, sir. We will discuss in if any interested sessions or maybe if you like to. Thank you once again. And
It's our pleasure.
very wonderful session deliver you. But that what we say. मतलब 2 दिन से हम राह देख रहे हैं कि सर कब आएंगे
थैंक
आज मौका हमको मिल गया
यू थैंक यू एक्चुअली हमारा सेशन अभी स्टार्ट हो गया ना तो फ्राइडे मेरी कल भी क्लास थी 6 to 8
अच्छा
तो अदरवाइज मैं कल ही आ जाता
अच्छा
और फिर मैंने नायक सर से कहा कि अगर मेरी क्लास कल 8 o'clock खत्म हो रही है तो मैं 8:30 से ले लेता हूँ सेशन 8:30 से 9:30 या 10 जब तक पर लेकिन आई थिंक आपका नहीं हो रहा था तो मैंने फिर ये सैटरडे के लिए रिक्वेस्ट
वो शेड्यूल थोड़ा सा आगे हो जाता था इसके लिए मैं बोला कि आज लेंगे
आज भी बराबर है
तो कुछ बात नहीं वैसे भी आज 8 8:15 बजे तक सेशन है ही हमारा तो अभी मतलब आपका लास्ट ही सेशन है तो इसके बाद इनका टेस्ट और ये लेंगे टेस्ट और फंक्शन है तो आप उसमें भी एक आधे घंटे के बाद ज्वाइन हुई है सर ओके थैंक यू सर थैंक यू
थैंक यू
Yes, sir. Yes, sir. So all participants, please give your test, which is already given, and link I was given for feedback link. Just wait.
Sir, test link is not opening, sir. Hello, sir.
Sir, already procedure is given on Atal FDP group. Please check.
Sir, see, it is not opening, sir, in that.
Sir, many participants are given here. That I am just taking feedback. Just shut down your PC and restart and then give, or otherwise use mobile app, please.
खुला नहीं हूँ मैं, 1-2 दिन में हो जाएगा वो, मेरा पेमेंट एक्चुअली अटका है ना, तो वो मैं करता हूँ। हाँ
भैया हेलो सर, 10 साल हो गया काम कर रही है आपके पास। ओके, हाँ इतना तो एडजस्टमेंट आता ही है ना मुझे।
नहीं अर्जेंट रहेगा तो मैं दोस्त से लेके मैं दे सकता हूँ आज के कुछ करता हूँ आपको अर्जेंट।
भैया आपको जब भी लगेगा ना तभी आप दे।
हेलो सर. हॅलो. हॅलो काटे सर.
हा मॅडम बोला ना.
हां, लॉग इन केल्यानंतर त्याच्यामध्ये असेसमेंट टॅबवर गेल्यानंतर तिथे टॅब जो आहे त्याच्यावर क्लिक केल्यानंतर तिथे 25 क्वेश्चन्स इन 60 मिनिट्स असं येतं, तेच ना?
हा तोच ना.
हां.
तोच आहे ना. ऍप्लिकेशन आयडी बघा ना, चेक करा ना, तिथे मी पाठवलंय आता ग्रुपला.
हां, ठीक आहे सर. थँक्यू सर.
पाठवलं की म्हणा. पाठवलं तुम्हाला व्हॉट्सअपला चेक कर. चेक कर.
Hello, sir. Kate sir. Kate sir.
येस सर, कोण आहे? हॅलो.
प्रोफेसर खान.
हा बोला सर.
सर ते टेस्ट चालू केलं आहे पण आन्सर
हा.
सेव्ह नाही होत आहे.
आन्सर सेव्ह होत नाही, बाकीच्यांचा होतंय सर. एकदा लॉग आउट करून लॉग इन करा परत.
बरं ठीक आहे. थँक्यू.
तेच ना, हळूहळू चाललंय.
हेलो काटे सर।
हेलो हेलो हेलो।
Come, sir. Hello.
Yes, sir.
Yes, sir. Yes.
I'm
So shall we start validatory function and participants feedback? Okay.
I'm in the middle of exam, sir. Yes, you can start, sir. We can start.
Yes, sir. Yes, sir.
Yeah.
I think Nikam sir is asking someone. Nikam sir.
Hello.
Yes, sir. Yes, sir. Wait.
I just want to give my feedback, sir, on
Okay.
this
Okay.
FDP.
Wait. 2 minutes. Wait.
Okay, sir.
So,
Okay, sir.
a very good evening to one and all. Thank you for all participants attending successfully this 6 days Atal FDP workshop. So, anybody can view their views, share their views regarding feedback as a feedback, and give suggestions for that we will next time improve us. So, please, anybody share their thoughts or views.
With your permission, can I, sir?
Yes, sir. Yes, sir. Please.
First of all, I must congratulate you, all of you, and we appreciate your hard work and efforts that you did during the last 5 days or 6 days. Although I also appreciate all the participants that they spare a valuable time from the daily routine life. Undoubtedly, I'm not from this domain. But yes, I just want to know about the building and all the sustainable things, which when I come across with the last few years, that FDP is totally amazing one, creating the best understanding from the previous till as of now date, which is topmost requirement in the present era. And I will definitely try to motivate others also to gain such kind of knowledge in such kind of FDPs. I appreciate Professor Gurumante Kate sir and Dr. Shrikant, and the really insightful session across the globe, a key speaker across the globe you collected. That's a amazing one. Thank you so much. That's what about my feeling. And the last session is almost the one which helps me to cherish my old memories. I heard about Kande and all the things.
Yeah.
Thank you so much.
Very thank you, sir. Very thank you. Yes. Yes, Vagisha sir.
Good evening, sir.
Good evening, sir. Good evening.
Sir, it was a very nice session. See, all the sessions were very nice. Actually, I don't know where from you got all the resource persons. See, they were all excellent, and we could learn a lot. I can just say it was a very nice session, sir. See, the whole FDP was very nice and nicely organized.
Yeah. Thank you, sir. Thank you.
Hello, sir.
Yes, sir. Yes, sir. Please.
Sir, I want to share my views about this Atal FDP arranged by SPPM COE. So I have attended Atal FDP in physical mode also, and this one now in online mode. So I don't feel any difference between physical mode and online mode because every session were well organized and the speakers were views on sustainability up to mark and beyond our expectation. So I would like to thank you, the organizers, and the whole team of SVPM COE.
Hello, sir.
Yes, sir.
Myself, Professor Suraj Jagtap. I'm also from Baramati. I'm very thankful to everyone, especially Dr. Kate sir, Dr. Mukde sir, Principal Dr. Mukde sir, for providing such a nice technical piece here. And starting from the first session and up to this Dr. Suresh Malla's last session, everything was excellent. Thank you. Thank you.
Okay.
Okay. Thank you, sir.
Thank you, sir. Yes.
Can I share, sir?
Yes, sir. Yes, sir. Please.
Okay, so this is Professor Prasad Nikam from Chhatrapati Engineering College, Ahilyanagar. So this FDP organized by Shivnagar Vidya Prasarak Mandal's College of Engineering, Malegaon, Baramati. So I would like to thank all the organizing team members, especially Dr. Gunwant Kate sir, Head of Civil Department, Dr. Shrikant Bobde sir, and also Dr. Chittaranjan Nayak sir, for successful organization of this FDP on building sustainable infrastructure for urban and social resilience, challenges and future pathways. So right from 5th January to 10th January, we have seen all the experts. They were really very knowledgeable persons from their field. And I think that definitely each participant, they have taken more than their expectation. So thank you very much, sir. So in future also we are expecting more from you. So thank you all of you, and thank the opportunity which given to me for sharing my views on this FDP. Thank you very much, sir.
Yes, sir.
Thank you, sir.
Thank you, sir. Yes, anybody else? Yes, Patil sir. Patil sir.
I request Kate sir, if possible, kindly arrange the same FDP in the similar ways in offline mode.
Okay. Okay, sir. Yes.
Thank you. Thank you, sir.
Hello.
Yes, madam.
Yeah. This is Dr. Manisha Wagmare from AISSMS College of Engineering, Pune. Sir, the workshop was very highly informative and engaging. It provided valuable insight that I can apply in my professional work as well. Though I am from structural engineering field, the content was still very relevant and helped me a lot in broadening my perspective. All the speakers explained the concepts very clearly and practical with practical examples, and encouraged meaningful interactions as well. That made the sessions very effective. Overall, it was well organized, and it shows the efforts that all the team has put in. The workshop was very beneficial. I genuinely appreciate the efforts taken by the organizers. Thank you.
Thank you, ma'am. Thank you.
Thank you. Thank you.
Yes, anybody? Yes. Patil sir, want you any share?
Hello, sir.
Yes.
Can I
Yes,
share
ma'am.
my feedback, sir?
Yes, yes, ma'am.
Okay, sir. Thank you, sir. I would like to express my sincere appreciation for organization such an excellent faculty development program. As a participant, I found the entire program to be highly beneficial, and we learn more things related to the environmental sustainability.
Yeah.
Thank you, sir.
Ma'am, your name and college, please.
Sir, my name is Vaishali Vijay Rokde. I am from AISSMS College of Engineering, Pune.
Polytechnic or degree?
Degree college, sir.
Okay, okay, okay.
Okay, sir. Thank you, sir.
Thank you.
Thank you.
Yes, Patil sir. Yes, yes. Sagar Patil sir, some sharing your thoughts. Hello. I think is not in range. Yes, anybody? Valuable suggestions are most welcome.
Sir, could you please share the study material?
Yeah, madam. Yeah. Within 2 to 3 days, their PPTs and video links are available on our WhatsApp group.
Okay, thank you, sir.
Yes, yes. Patil sir? I think Patil sir have not range. बघ ना ते इकडे बाहेर. Okay.
Hello.
Yes.
Hello. Can I speak, sir?
Continue. Yes. Continue.
Okay. So I am Jaideep Yadav from SVPM College of Engineering, Malegaon, Budruk only. So, firstly, this subject selected by the coordinators was very good regarding the about the people, safety, and future of the societies. And also, all the speakers explained the subject in a very simple and easy to understand languages. Sessions were quite interactive and also discussions were very fruitful. Practical ideas were discussed and helped us realize our responsibilities towards the sustainable development, which is the need of our. Overall, the session was inspiring and motivating. It increased our awareness and in future it will contribute to build a strong, safe and sustainable cities for future generations. And cherry on the cake, the last session was very good on the sustainability point of view. Once again, thank you to all the coordinators and those who supported them. And hopefully we will get more such FDPs regarding this. So thank you.
Thank you, sir.
Thank you, sir. Yes, Girish Patil sir, Sagar Patil sir, want to yes, sir, shares. Bobde sir,
Okay.
can we conclude?
Yes, sir.
Yes, sir.
A warm good evening to all for this valedictory session. myself, Dr. Srikant Bobde, Assistant Professor, Department of Civil Engineering, and my colleagues, Dr. Unwan Kate sir, coordinator of this Atal online 6-day faculty development program. I would like to express my sincere gratitude to everyone who made this program meaningful and successful. I sincerely thankful to our President, Honorable Mr. Sharad Chandraji Pawar Sahib, Vice President and Deputy Chief Minister, Honorable Mr. Ajit Dada Pawar Sahib, all trustees, directors, Honorable Secretary, Dr. Thombre sir, Principal, Dr. Mukne sir, Head of the Civil Department, Dr. Bisema, distinguished faculty members, dear colleagues, and esteemed resource person from the globe. As we reach the valedictory session of this FDP on building sustainable infrastructure for urban and social resilience, challenges, and future pathway. It is a moment of reflection, gratitude, and renewed commitment over the past 6 days, starting from Dr. Lakhankar sir, New York, USA, to Dr. Bhalla sir, IIT Delhi. This program has provided us with an enriching platform to explore critical issues that shape the future of our cities and communities. These days have truly been our cities and communities. This day has truly been a journey of learning, reflection, and professional growth. The deliberations during this FDP have highlighted the pressing challenges faced by urban and social infrastructure, rapid urbanization, climate change, resource constraints, and increasing the vulnerability for communities. At the same time, the session offered insightful discussion on sustainable design, resilient infrastructure systems, green construction practices, smart technologies, and policy framework that can guide the future development. We are deeply grateful to our respected resource persons who generally share their knowledge, experience, and expertise. Their sessions not only enhance our academic understanding but also motivated us to strive for the excellence in our professions. Once again, I sincerely thankful to our management, secretary, principal, head of the civil department, and department support to success of this 6-day faculty development program. Thank you. Thank you all. Over to you, Kate sir. Kate sir. Kate sir is not audible.
Yes, sir. Yes, sir. Please. Myself, Dr. G.K. Kate. I am Atal FDP coordinator of this building sustainable infrastructure for urban and social resilience challenges and future pathways, which is conducting from last 5th January to till date, 10th January of 2026. So respected all participants, chief guests, then distinguished resource person, then organizing committee, my colleagues, and all dear participants. So one and all, very good evening to all. As we welcome to this conclusion of enriching this online FDP, which gives me immense pleasure address this valedictory function to reflect the journey of this past 6 days. This was FDP was truly rewarding experience, academically stimulating, professionally empowering, intellectually engaging, also as well as bridging the gap between academia and industry. And the real sessions were thoughtfully designed and delivered with great clarity, relevance, and depth. Each resource person brought valuable insights, practical perspectives, and contemporary approaches that will undoubtedly influence our teaching, research, and professional practice. So I would like to express our sincere thanks to all resource persons who generously shared their thoughts, expertise, and experiences in this Atal FDP. So all the sessions are enhanced our knowledge, but also inspired in think critically, innovate, and continuously evolve as educators, because education is a continuous process. So I also like to acknowledge the all participants whose active involvement, thoughtfully questions, and enthusiastic participation made this FDP lively and interactive, despite that our diverse locations, that platform is meaningful collaboration and collective learning. Especially thanks for this Wagmare madam, then Umang sir, then also Wagesh sir, then also many more participants. They are each and every session at the end asking some their queries, questions, and so many. So thank you all this. Also, last we conclude the member of that truly value of this FDP lies not only in the certificates we receive, but in how we apply the knowledge and skills gained into our classroom, research endeavors, and institutional development. Because institutional development is very, very important on point of view, this FDP. So again, I lastly, once again, thanks to everyone who contributed this success of this program by our President Pawar sir, then Vice President Sri Ajit Pawar sir, then management all, then Secretary Sri Thombre sir, Principal Mukne sir, and our department head Dr. Bisse madam, and lastly our all department support, civil engineering department support. So I hope this professional connection from here continue beyond this FDP and lead to future collaborations. So thank you for all your time, commitment, and participation. So wishing everyone continued learning, growth, and success. So thank you, and thank you. Wonderful day ahead. So thank you. Over to you, Ingle madam.
Thank you, Kate sir. A warm good evening all. I am Dr. Sujata Bise ma'am, head of the department. So, respected distinguished resource person, honorable secretary, esteemed members of the management, respected principal, program coordinators, faculty member, and dear participant. At the outset, I feel honored to address the gathering at the valedictory section of the Atal Online 6-day Faculty Development Program on the Building Sustainable Infrastructure for Urban and Social Resilience Challenges and the Future Path. I would like to express my deep sense of gratitude to our Honorable Secretary, the respected management, and our respected Principal Sir, whose constant encouragement, vision, and timely permission made it possible for Civil Engineering Department to organize this FDP. I would like to place on record my heartfelt thanks to AICT Atal Academy for approving and supporting this FDP, and experts who share their valuable knowledge and real-world experience, whose expert lecture added immense value to this program. Their insights have certainly bridged the gap between theory, research, and professional practice. I also congratulate the program coordinator, Dr. Gunwanta Kate sir, and co-coordinator, Dr. Srikant Bobde, and the organization committee for their meticulous planning, smooth executions, and dedication, which ensure the success of this program. On behalf of Civil Engineering Department, I thank all participants for their enthusiastic involvement, active discussion, and commitment throughout the program. I conclude by expressing my hope that such academic interaction will continue in future, fostering the collaboration, innovation, and excellence in civil engineering education and the research. Thank you all. I wish you continued success in your professional journey. Thank you once again. Over to Kate sir. Kate sir.
Yes, yes. Our principal sir with also. Principal sir Mukne sir, please sir.
Thank you.
Sir, your voice is not reaching here.
Sir. Good evening to all. Am I audible?
Your voice is, sir, something.
Is it audible now?
Sorry, your voice is interrupt, sir.
Voice is interrupting, sir. Just switch off video and
I think you might have not range, sir.
Maybe.
Maybe. Sir, please switch off video and continue.
Yeah. Is it now audible?
Yes, sir. Yes, sir.
Yes, sir.
Yes. Good evening, all participants and resource person. So I was that listening to the feedback given by the participants, and based on the feedback, I would like to congratulate Dr. Kate sir, Bobde sir, and Civil Engineering Department for organizing such a FDP, which I think enriched the knowledge of all the participants. So this topic is also, I think, relevant to the newcomers also, and those are experienced in civil engineering for them also, because topic, I think, dealt with the future civil engineering roadmap, we can say. So, and that's why the learning happened in this particular FDP might become useful in your professional journey. So the motto of Atal FDP, the motto behind arranging this FDP, and whatever objective set by the AICT for organizing such kind of FDP, I think that objective has fulfilled, because whatever feedback you have given, from that I conclude that the sessions were really meaningful and which was adding value to your professional career. So, and such kind of programs, I hope, will come from the civil engineering department in future also. So without taking much of your time, I express on behalf of college, all the resource persons and participants for attending this wonderful FDP. Thank you.
Thank you, sir. Kate sir, unmute.
All the participants are requested, please on your videos. So we have to take a photograph. Yes. So all the participants are requested. Your certificate may be generating after giving feedback and successfully test completed. So it may use time within 2 to 3 days or maybe 1 day, 2 days. So just a minute. Okay. Thank you all. Thank you. Thank you. Thank you all. Thank you all participants. The session will concluded and thank you.
Good evening, Mukne sir.
Good evening, Vagisha sir. I hope you enjoyed this session.
Yeah, sir. Nicely enjoyed.
Yes, sir. Every session was enjoyed by sir because they actively participated. Vagisha sir, Wagmare madam, then also Umang Bharatwal, which is from Rajasthan.
Thank you, sir.
Thank you. Thank you, madam.